What if I told you that the universe around you, the chair you're sitting on, the screen you're watching, even the air you're breathing, is constantly shimmering with invisible energy, flickering in and out of existence in a dance so strange it defies everything we think we know about reality? This isn't science fiction. It's the startling truth behind one of the most profound mysteries in modern physics, the world of quantum fluctuations. At the tiniest scales imaginable, empty space isn't empty at all. Instead, it's a bubbling, chaotic sea of virtual particles popping into and out of existence so quickly we can barely detect them, a phenomenon physicists call quantum foam. And it's within this hidden layer of reality that some of the most radical and breathtaking ideas about our universe are born. Today, we're diving deep into this unseen world, exploring 30 astonishing theories about quantum fluctuations that stretch the limits of imagination. From the birth of universes to the nature of time itself, these ideas don't just challenge our understanding of physics. They invite us to reconsider what is real, what is possible, and whether the fabric of existence might be far more dynamic and unpredictable than we ever dreamed. This isn't just a topic for scientists in lab coats. It's a journey into the heart of reality, one that touches on questions we've all asked ourselves under a starry sky. Why is there something rather than nothing? How did everything begin, and what hidden forces are at work behind the scenes of our everyday experience? So settle in, open your mind, and get ready to venture into the quantum foam, a realm where particles flicker like fireflies in the dark, where empty space breathes with potential, and where the answers we find might just reshape how you see everything. Whether you're new to these concepts or you've been fascinated by them for years, what lies ahead will surprise, inspire, and maybe even unsettle you in the best way possible. Because this isn't just a story about science, it's an exploration of the very foundations of existence, and by the end, nothing may look quite the same. Our journey begins with a concept so fundamental, it redefines the very meaning of nothingness. Imagine the most perfect vacuum you can, a region of space completely emptied of all matter, every single atom and particle sucked out. For centuries, we believed such a void would be a place of absolute stillness, a pure and silent nothing. But the quantum world had a stunning surprise in store. We now know that even this so-called emptiness is alive with activity. It's filled with a seething, chaotic energy that never rests, a background hum to the universe known as the zero-point energy field. This isn't energy in the way we typically think of it. It's the baseline, the absolute lowest possible energy state that any physical system can have. And according to quantum mechanics, that lowest state is not zero. It's a constant, frantic vibration. The term itself has its roots in the work of the great physicist Max Planck, the father of quantum theory, around the year 1912. He was studying the behavior of light and discovered that even at a temperature of absolute zero, the point where all classical motion is supposed to freeze solid, this faint residual energy would still persist. It was a baffling idea, energy that couldn't be removed, a perpetual motion woven into the fabric of space itself. This concept was later refined by none other than Albert Einstein and his colleague Otto Stern in 1913. Their work helped solidify the idea that this zero-point energy wasn't just a mathematical quirk but a real, physical phenomenon. They realized this energy is the reason liquid helium remains a liquid all the way down to absolute zero, refusing to freeze solid because the atomic jitter from this field is too strong. Think of it like a car engine that's always idling, even when the vehicle is parked and turned off. It never truly shuts down. This quantum jitter is that eternal idle for the entire cosmos. This leads us to the most dramatic manifestation of this field, the spontaneous creation of virtual particles. The zero-point energy field is constantly borrowing energy for unimaginably tiny fractions of a second to create pairs of particles and their antimatter counterparts. They flicker into existence and then almost instantly annihilate each other, returning the energy they borrowed. It's a constant popping foam of creation and destruction happening all around us, trillions of times in every cubic centimeter of space every second. This is the quantum foam we mentioned, and it means that what we perceive as serene, empty space is actually the most dynamic and active place imaginable. It's the foundation upon which every single thing is built, the hidden stage upon which the drama of our universe plays out. And if the vacuum of space is this seething sea of potential, what happens when you place the most destructive force in the universe right in the middle of it? This brings us to one of the most elegant and groundbreaking theories to emerge from the study of quantum fluctuations, Stephen Hawking's incredible prediction of black hole evaporation. It's a concept that connects the impossibly small world of quantum mechanics with the immense gravity of black holes, and it all starts with those virtual particle pairs we just discussed. Normally, these particle-antiparticle pairs borrow energy from the universe, exist for a fleeting moment, and then collide, annihilating each other and paying the energy back. It's a perfect, balanced transaction that happens everywhere all the time. But place this event right at the precipice of a black hole, a point of no return known as the event horizon, and that perfect balance is shattered. Imagine one of these virtual pairs spontaneously appearing just outside the black hole's edge. In a devastatingly precise cosmic robbery, the black hole's immense gravity can tear the pair apart before they have a chance to annihilate. One particle gets snatched and pulled across the event horizon, forever lost inside the black hole. Its partner, however, gets flung away into space, now a real particle with real energy. From the perspective of someone watching from afar, it looks as if the black hole has just emitted a particle. This is Hawking radiation, but here's the truly mind-bending part. The particle that fell in had negative energy. To conserve overall energy, the black hole itself must lose a tiny amount of mass to account for the positive energy of the particle that escaped. So, while the black hole is seemingly emitting radiation, it's actually slowly losing mass, getting smaller and hotter over unimaginable stretches of time. This was a revolutionary idea. It meant black holes aren't the eternal prisons we once thought. They have a lifespan. They slowly, gradually evaporate, and this process provides a profound clue that quantum mechanics and general relativity, the two pillars of modern physics, are deeply intertwined, even if we don't yet have the full theory to describe how. But if Hawking's work showed us how the quantum world can gently erode a black hole, it opens up an even more profound and troubling question about the energy inherent in empty space itself. This brings us to what many physicists consider the most embarrassing problem in all of theoretical physics, the cosmological constant problem. It's a puzzle so vast it concerns the ultimate fate of the entire cosmos, and it starts with a simple, terrifying calculation. We just explored how the zero-point energy field is brimming with activity. Every possible vibration, every possible frequency of a quantum field is constantly humming, contributing a tiny bit of energy to every point in space. When theorists try to add up all this energy from every conceivable quantum fluctuation, the result is a number so catastrophically large it defies comprehension. The theoretical prediction suggests that the vacuum of space should possess an energy density of around 10 to the power of 112 joules per cubic meter. This isn't just a big number, it's an energy level so intense that it would generate a repulsive force of such magnitude that the universe would have ripped itself apart nanoseconds after the Big Bang. Not a single atom, let alone a star, planet, or person, could ever have formed. Yet, when astronomers look out at the universe, they measure the actual energy density of empty space. This observed value, often called dark energy, is incredibly small and positive, causing the universe's expansion to accelerate, but at a very gentle rate. The measured value is about 10 to the power of -9 joules per cubic meter. So we have a problem. The theory predicts a number, and observation gives us a completely different number. The discrepancy between them isn't just a small rounding error. It's a factor of 1 followed by 121 zeros. This is the largest and most notorious mismatch between theory and experiment in the entire history of science. To put that number into perspective, it's a greater difference than the scale between the size of a single proton and the size of the entire observable universe. This isn't just a mathematical inconvenience, it strikes at the heart of our understanding. How can our two most successful theories, quantum mechanics and general relativity, be so spectacularly wrong about something so fundamental? One proposed solution is a concept called supersymmetry, an elegant theoretical idea which suggests every known particle has a hidden superpartner particle. In a perfectly supersymmetric universe, the positive and negative contributions of these particle pairs to the zero-point energy would cancel each other out exactly, leaving a vacuum energy of zero. The problem is, we don't live in that perfect universe. If supersymmetry exists, it's a broken symmetry, meaning those partner particles are too heavy for us to have detected yet, and the cancellation is frustratingly imperfect, leaving us with this enormous discrepancy. Other physicists have wondered if the answer lies not in cancelling the energy, but in questioning our understanding of gravity itself. Perhaps gravity doesn't couple to vacuum energy the way our current equations suggest. Or maybe the value isn't a fixed constant, but is instead an environmental effect, a result of our specific place in a much larger multiverse. In this anthropic landscape, most universes would have a cosmological constant so large they instantly blow apart, or so negative they immediately collapse. We find ourselves in one of the impossibly rare Goldilocks universes where the value is just right for galaxies and life to form, simply because we couldn't be here to observe it otherwise. It's a controversial idea, suggesting that some fundamental constants might not be derived from elegant equations, but are instead random environmental variables. This immense gap between prediction and observation remains a stark reminder that for all our knowledge, we are still missing a crucial piece of the puzzle, a deeper theory that can truly unite the quantum world with the cosmos at large. And that staggering discrepancy between the predicted and observed energy of empty space sets the stage for one of the most successful theories in all of cosmology, a theory that credits these very same quantum fluctuations with creating everything we see in the night sky. This brings us to the incredible story of cosmic inflation and how the smallest possible vibrations became the blueprint for the entire cosmic web. The theory of inflation proposes that a fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. For a fleeting moment, it was stretching faster than the speed of light, smoothing out and flattening the entire cosmos. But it wasn't a perfectly smooth process. Remember that seething quantum foam, the constant jitter of the zero-point field? That chaos was there at the very beginning, imprinted on the fabric of spacetime itself. As the universe inflated at a staggering rate, it didn't just stretch space. It stretched those tiny, random quantum fluctuations in the energy field that was driving the expansion. Think of it like blowing up a balloon that has a barely noticeable microscopic texture on its rubber. As you inflate the balloon to an enormous size, those tiny, random bumps and wrinkles are stretched into vast, continent-sized features. In exactly the same way, the infinitesimal quantum jitters in the early universe were magnified from the quantum scale to an astronomical scale. These stretched fluctuations became slight variations in density, tiny pockets where there was just a little more matter and energy, and other pockets where there was a little less. Once the period of inflation ended, the universe settled into the more familiar expansion we see today, but it was now imprinted with these fossilized quantum ripples. Gravity got to work on these imperfections. Over hundreds of millions of years, the slightly denser regions had stronger gravitational pull, slowly attracting more and more matter from the surrounding areas. These regions became the seeds for future cosmic structure, the first clumps of dark matter that would eventually pull in gas to form the first stars, then galaxies, and then immense clusters of galaxies. The most stunning evidence for this incredible story is etched across the entire sky. When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, we are essentially taking a baby picture of the universe when it was just 380,000 years old. This image isn't a featureless blank slate. It's covered in tiny temperature variations, hotter spots and colder spots, differing by only about 1 part in 100,000. These minuscule differences map directly onto those original density fluctuations. The hotter spots correspond to those slightly denser regions, the seeds that inflation planted. The pattern of these spots, their size and distribution, matches the prediction of quantum fluctuations being stretched by inflation with astonishing precision. It is perhaps the most compelling link we have between the quantum world and the cosmos at large. A direct line from the tiniest flicker of nothing to the grand tapestry of galaxies, including our own Milky Way. We are literally the children of quantum noise, the result of randomness amplified to a cosmic scale. But for all the grandeur of cosmic inflation and the cosmic microwave background, how do we know for sure that this quantum foam, this sea of virtual particles, is anything more than a beautiful mathematical idea? How do we prove that empty space is truly alive with energy? The answer lies not in looking out at the distant cosmos, but in a remarkably elegant and direct experiment you could, in principle, conduct on a tabletop. This brings us to the Casimir effect, one of the most stunning validations of quantum theory, where the ghostly whisper of quantum fluctuations pushes on real, solid objects. The story begins in 1948 with a Dutch physicist named Hendrik Casimir. While working at the prestigious Philips Research Laboratory, he was pondering a fascinating consequence of quantum field theory. He knew that even a perfect vacuum is filled with a spectrum of fluctuating electromagnetic waves, every possible wavelength, from the incredibly long to the vanishingly short, is constantly flickering into and out of existence. These waves are the electromagnetic manifestation of the virtual particle pairs we've been discussing. Casimir asked a brilliantly simple question. What would happen if you placed two perfectly smooth, uncharged, parallel metal plates extremely close together in this vacuum? His theoretical calculations revealed something extraordinary. The presence of the plates restricts the types of electromagnetic waves that can exist in the gap between them. Only those waves whose wavelengths fit perfectly between the plates, meaning a half wavelength or a full wavelength, must equal the gap distance, are allowed to persist. Outside the plates, however, all possible wavelengths can still flicker and fluctuate without any restriction. This creates an imbalance in the radiation pressure. There are simply more virtual particles and waves pushing on the outside surfaces of the plates than there are pushing on the inside surfaces. The net result is that the two plates are pushed together by the relentless pressure of the quantum vacuum itself. This tiny, attractive force between the plates is the Casimir force. For decades, it remained a fascinating theoretical prediction, a neat bit of quantum weirdness. The force is incredibly small. To detect it, the plates need to be placed only a few micrometers apart, a distance comparable to a fraction of the width of a human hair. Manufacturing plates that smooth and positioning them that precisely without any electrical or gravitational interference was a monumental technical challenge. It wasn't until 1997, nearly 50 years after Casimir's proposal, that a team at the University of Washington, led by Steve Lamoureux, conducted a landmark experiment that achieved the necessary precision. Using a gold-coated spherical lens and a flat plate instead of two parallel plates to avoid alignment issues, they measured the force directly. Their results matched Casimir's predictions with an uncertainty of less than 5%. The quantum vacuum was no longer just a theory, it had left its fingerprint in a lab. this wasn't just a one-off curiosity. Subsequent experiments have only made the evidence more ironclad. Scientists have even measured the Casimir force for different materials and geometries, and the effect changes exactly as quantum electrodynamics says it should. It stands as one of the most direct pieces of evidence we have for the reality of zero-point energy and quantum fluctuations. It proves that nothing has a structure, a texture that can influence the world of the very small. This isn't an abstract energy field. It's a tangible force that nano-engineers must now account for when designing microscopic machines, as at tiny scales, the Casimir effect can cause components to stick together. From a profound prediction about the nature of reality to a practical consideration in modern technology, the Casimir effect bridges the gap between the deepest questions of physics and the tangible world we can measure and touch. But if the Casimir effect shows us that empty space has a measurable structure, what does that structure actually look like at the very smallest scales imaginable? To answer that, we have to venture down to a realm so tiny it defies visualization, to a theory that suggests the very fabric of reality is fundamentally rough and chaotic. This brings us to John Wheeler's mind-bending spacetime foam theory, a concept that proposes the universe is built on a foundation of pure turbulence. John Wheeler was one of the 20th century's most visionary physicists, a man who helped design the hydrogen bomb, coined the terms black hole and wormhole, and mentored a generation of brilliant thinkers. In the 1950s, he turned his formidable imagination to the implications of combining quantum mechanics with general relativity. He realized that if the energy of the vacuum is constantly fluctuating, as the Casimir effect proves, then gravity, which is the curvature of spacetime by energy and mass, must also be fluctuating. At scales we experience every day, spacetime appears beautifully smooth and continuous, like a calm ocean. But Wheeler proposed that if you could zoom into the absolute smallest possible scale, a distance known as the Planck length, this serene picture would completely vanish. The Planck length is almost inconceivably small. It's about 1.6 times 10 to the power of -35 meters. To even begin to grasp this, consider that the size of an atom is to the Planck length what the size of our entire solar system is to an atom. At this unimaginably tiny scale, Wheeler argued, the violent fluctuations of the quantum vacuum would cause spacetime itself to become wildly distorted. The geometry of space would cease to be smooth and would instead become a chaotic, frothing mess, a bubbling foam of tiny, transient wormholes and ever-changing topological fluctuations. In this spacetime foam, the very concepts of before and after, or here and there, lose their clear meaning. It would be a realm of pure quantum chaos where tiny regions of space are constantly pinching off and reconnecting, bubbling and boiling with the raw energy of creation and annihilation. This idea isn't just a wild speculation. It emerges naturally when we consider the fundamental limits of measurement dictated by quantum mechanics and gravity. Werner Heisenberg's uncertainty principle tells us we cannot precisely know both the position and momentum of a particle. To measure the position of an object with extreme accuracy, you have to hit it with a photon of very high energy, a very short wavelength. But pack too much energy into a tiny region of space, and according to Einstein's general relativity, you risk creating a tiny black hole, an event horizon that would swallow your measurement probe and any information it could hope to retrieve. This creates a fundamental lower limit to how small a region of space we can ever probe. The Planck length represents that ultimate barrier, the point at which our very tools of observation break down, and the classical idea of a smooth, continuous spacetime simply ceases to be meaningful. Wheeler's foam theory has a profound implication. It suggests there is a fundamental limit to the precision of reality itself. It's not just that our microscopes aren't good enough, it's that the universe is inherently fuzzy at its core. The foam would act like the grain on a piece of photographic film, No matter how high the resolution of the film, if you zoom in far enough, you'll eventually see the individual grains that make up the image. In the same way, our smooth, continuous universe is a large-scale average of an underlying, chaotic, and discrete foam. This means that if you tried to measure a distance with an accuracy finer than the Planck length, the act of measurement would be disrupted by the foam's violent fluctuations. The spacetime you're trying to measure would be roiling so violently that the concept of a definite distance would no longer hold. While we cannot directly observe spacetime foam, some ingenious experiments have tried to detect its subtle effects. One approach involves studying the light from incredibly distant quasars and gamma-ray bursts that have traveled across the universe for billions of years. If spacetime is foamy, it should act like a subtle fog for light, causing tiny, random delays in the arrival time of photons of different energies. It would be an effect somewhat similar to light twinkling as it passes through the turbulent atmosphere of Earth, but on a cosmic scale. So far, these observations have only placed upper limits on the foaminess, suggesting that if foam exists, its effects are even smaller than the Planck scale for the low-energy photons we can detect. But the search continues, as confirming the existence of this fundamental graininess would be one of the most monumental discoveries in physics, finally revealing the true, chaotic heart of reality. This concept of a seething, active vacuum, so vividly demonstrated by the Casimir effect and theorized in spacetime foam, leads us to one of the most profound and pressing mysteries in all of cosmology. We've seen how quantum fluctuations shape the beginning of everything, but could they also be determining the ultimate fate of the universe? This brings us to a theory that attempts to connect the quantum world to the largest scales imaginable. The proposal that the energy of the quantum vacuum itself is the mysterious force we call dark energy. The story of dark energy's discovery is one of the great surprises in modern science. For most of the 20th century, cosmologists believed the universe's expansion, set in motion by the Big Bang, was gradually slowing down due to the relentless pull of gravity. The main question was whether that slowdown would eventually lead to a big crunch or just a gradual, eternal coasting. Then, in the late 1990s, two independent teams of astronomers were studying distant supernova exploding stars that serve as cosmic mile markers to measure this deceleration with unprecedented precision. To their absolute astonishment, they found the opposite. The expansion of the universe wasn't slowing down at all. It was speeding up. Some mysterious, repulsive force was working against gravity, pushing galaxies apart at an ever-increasing rate. This discovery earned the teams the Nobel Prize in Physics in 2011 and introduced the world to the term dark energy. The immediate and seemingly elegant candidate to explain this force was something physicists already knew about in theory: the cosmological constant. This was a term Einstein had originally inserted into his equations of general relativity to allow for a static universe, which he later called his greatest blunder after Edwin Hubble discovered the universe was actually expanding. But with this new discovery, the cosmological constant was resurrected. It represented a constant energy density inherent to the fabric of space itself. As the universe expands and more space comes into existence, this vacuum energy density remains constant, meaning its repulsive gravitational effect grows stronger over time, eventually dominating over the weakening pull of matter. And what could be the physical source of this constant energy density? The most natural answer seemed to be the zero-point energy of the quantum vacuum, the very same sea of virtual particles we've been exploring. It's a beautifully simple and compelling idea. The same quantum fluctuations that gave rise to the seeds of galaxies are also driving the universe's final act. There's just one catastrophic problem, and it brings us back full circle to the cosmological constant problem we discussed earlier. The calculated energy density from all known quantum fields is around 120 orders of magnitude. That's a 1 with 120 zeros after it, larger than the observed value of dark energy. If the quantum vacuum energy were actually that immense, the repulsive force would have been so unimaginably powerful that it would have ripped apart every atom, planet, and star instantaneously after the Big Bang. The universe as we know it would never have formed. The fact that we exist to observe a universe that is, in fact, gently accelerating means the actual value is almost zero, but not quite. It's a value so fine-tuned it borders on the miraculous. This enormous discrepancy is more than just a calculation error. It represents a fundamental crisis in our understanding of physics. It suggests one of two deeply unsettling possibilities. Either we are profoundly misunderstanding the nature of the quantum vacuum and how its energy gravitates, or dark energy is something entirely different from vacuum energy. Some theorists have proposed mechanisms for why the quantum vacuum's energy might not gravitate in the way we expect, perhaps due to some hidden symmetry or a novel property of gravity that only becomes apparent on cosmic scales. Others argue that dark energy might be a dynamic field, similar to the inflattened field that drove the early universe's rapid expansion, which has slowly evolved over billions of years to begin dominating the cosmos now. This idea is often called quintessence, a new fifth fundamental force that changes over time. The challenge in solving this puzzle is immense because it sits squarely at the intersection of our two most successful yet incompatible theories, quantum mechanics and general relativity. To truly understand dark energy, we likely need a complete theory of quantum gravity, something that has eluded physicists for a century. The implications are staggering. If dark energy is the quantum vacuum, its incredibly small positive value might be the ultimate anthropic coincidence, a random number that had to be almost exactly what it is for us to exist. If it's something else like quintessence, we are on the cusp of discovering a new fundamental component of reality. Current and future telescopes like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope are designed to measure the expansion history of the universe with even greater precision, hoping to detect any slight change in the strength of dark energy over time, which would be a telltale sign of a dynamic field rather than a static vacuum energy. The answer will determine not just the fate of the universe, but whether we need to rewrite the textbooks on the very nature of nothingness itself. Now, if the nature of particles themselves can be warped by gravity near a black hole or by the very structure of empty space, could something as fundamental as motion also change what we perceive to be real? This startling possibility is at the heart of our next theory, a concept that profoundly challenges the very definition of a particle and suggests that reality itself might depend on your state of motion. It's called the Unruh effect, named after the Canadian physicist Bill Unruh, who proposed it in 1976, and it emerges from a fascinating fusion of quantum theory and Einstein's special relativity. To understand the Unruh effect, we first need to revisit a cornerstone of quantum field theory, the idea that a vacuum isn't truly empty. For an observer floating inertially in space, not accelerating, just moving at a constant velocity, the vacuum is that seething sea of virtual particles we've discussed. This observer, in their frame of reference, would measure no real particles around them. They see only the fleeting, unpredictable dance of quantum fluctuations. But Unruh asked a revolutionary question. What would a different observer see? Specifically, what would an observer who is constantly accelerating perceive? Imagine two astronauts in the vast emptiness of space. One is simply drifting, coasting along comfortably. The other is strapped into a rocket ship with its engines firing at a constant, relentless rate, forever accelerating faster and faster. According to the Unruh effect, these two astronauts would have a completely different experience of the quantum vacuum surrounding them. The drifting astronaut, our inertial observer, confirms the expected quiet of empty space. But the accelerating astronaut would find themselves immersed in a warm bath of real particles. Their high-tech particle detector would click and buzz, registering a flux of real photons and other particles coming at them from all directions. It would appear to them as if they were flying through a region of space filled with a faint, heat-like radiation. This is UNRA radiation. Where are these particles coming from for the accelerating observer? The mind-bending answer is that they are coming from the same quantum vacuum that appears empty to the drifting astronaut. The acceleration itself is what makes the difference. It effectively warps the astronaut's perception of space-time, pulling real particles out of the quantum foam. The temperature of this perceived radiation is directly proportional to the acceleration. The harder you push the engines, the hotter this bath of particles becomes. For the accelerations we can achieve with even our most powerful rockets, this temperature is unimaginably cold, a tiny fraction of a degree above absolute zero, making it utterly undetectable in any practical experiment today. To feel a noticeable warmth, say room temperature, you'd need an acceleration of about 2.5 times 10 to the power of 20 meters per second squared. An acceleration so brutal it would instantly crush any known material and any human being into pulp. This effect isn't just a mathematical curiosity, it has a profound and deeply philosophical implication. It tells us that the concept of a particle is not an absolute objective truth. Whether or not a particle exists, whether it is real, depends entirely on the state of motion of the observer detecting it. What is a harmless quantum fluctuation to one person is a tangible, detectable particle to another. This shatters the classical, intuitive notion that the universe is filled with a fixed number of objects that everyone can agree on. At the quantum level, reality is observer-dependent. The UNRA effect is mathematically very closely related to Hawking radiation. In the case of a black hole, the intense gravitational field at the event horizon plays a role analogous to the acceleration in the UNRA effect. An observer falling into a black hole would see nothing special at the event horizon, while a stationary observer hovering outside using rockets to avoid falling in would detect the Hawking radiation. This connection beautifully illustrates how acceleration and gravity are intertwined, as Einstein taught us with his equivalence principle, and how this connection extends right down into the quantum realm. This radical relativity of particles forces us to ask an even deeper question. If reality is so different for observers in different states of motion, what does that say about the fundamental laws of physics? It suggests that the most basic building blocks of our universe are not little balls of matter but rather excitations in underlying quantum fields. And the existence of these excitations, these particles we hold so dear, is a matter of perspective, a consequence of how we interact with those fields. The UNRA effect doesn't just show us a new phenomenon. It challenges us to rethink what is fundamentally real in a universe where the vacuum itself is alive with possibilities. This very idea of a reality that shifts with perspective brings us to one of the most fundamental and perplexing features of our own experience, the relentless one-way flow of time. Why do we remember the past but not the future? Why does an egg scramble so easily yet never spontaneously unscramble itself? This is the mystery of the arrow of time, and some of the most compelling theories suggest its origin might be found in the same quantum chaos we've been exploring. On a microscopic scale, the fundamental laws of physics are almost entirely time-symmetric. If you were to watch a film of two electrons colliding and bouncing apart, and then you played that film backwards, it would look just as plausible and obey all the same physical laws. The equations governing particles work perfectly well whether time is running forwards or backwards. Yet on our human scale, the world is blatantly and obviously asymmetric. We are born, we age, we die. We see cups fall from tables and shatter, but we never see the pieces gather themselves up and leap back into our hands. This stark difference between the microscopic reversibility and macroscopic irreversibility is the central puzzle of the arrow of time, and many physicists believe the ultimate culprit is entropy. Entropy, at its heart, is a measure of disorder or randomness. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Things move from a state of order to a state of disorder. This is why your clean room gets messy over time, and why heat flows from a hot object to a cold one, never the reverse. But here's the crucial question. Why was the entropy of the universe so incredibly low in the first place? To have an arrow of time that points in a definite direction, the universe must have started in a state of exquisite order, a highly improbable configuration that had nowhere to go but towards greater disorder. This is where quantum fluctuations and the initial conditions of the cosmos become absolutely paramount. The dominant theory, as we discussed, is cosmic inflation. That period of hyper-fast expansion didn't just magnify quantum fluctuations into galaxies, it also created an environment of incredibly low entropy. Think of it this way: imagine a brand new deck of cards perfectly sorted by suit and in numerical order. This is a state of very low entropy. If you drop this deck, it will scatter into a random, disordered mess, a state of high entropy. The act of dropping it is irreversible. Now, what inflation did was essentially create that perfectly sorted deck for the entire universe. It took the primordial cosmos and stretched it out into an extremely smooth, uniform, and therefore highly ordered state. This was the ultimate low entropy starting point. From that moment on, the universe could only evolve in one direction, towards higher entropy, greater disorder. This ever-increasing entropy is what we perceive as the forward march of time. But this just pushes the question back a step. Why was the pre-inflationary universe in such a special, low-entropy state? Some theorists, like the late physicist Sean Carroll, propose that quantum fluctuations are the key. In the frantic chaos of the earliest moments, the universe was a hot, dense soup where quantum effects dominated. Fluctuations were happening everywhere. The idea is that one particular, rare fluctuation, a random, statistical dip in entropy, could have created just the right patch of space with the right conditions to trigger inflation. In this view, our entire observable universe, with its arrow of time, is the result of a single, incredibly fortunate quantum fluctuation that broke the symmetry and set everything on an irreversible path. This connects to a fascinating idea known as the past hypothesis, which simply states that the universe began in a state of low entropy. The quantum fluctuation theory gives a potential mechanism for how that initial state could have arisen from pure randomness. It suggests that the arrow of time isn't written into the fundamental laws of physics, but is instead an emergent historical property, a cosmic accident that was frozen into place by the rapid expansion of inflation and has been playing out ever since. We don't experience time flowing because of a law that commands it. We experience it because we are living in the aftermath of a very specific and unlikely quantum event. Our memories, our sense of cause and effect, and our very consciousness are all woven from this irreversible slide into disorder that began with a flicker in the quantum foam. But if the arrow of time emerges from the initial low entropy state of our universe, a state potentially born from a quantum fluctuation, it forces us to confront an even more radical possibility. What if our entire perception of a three-dimensional reality, complete with its flow of time and its quantum jitter, is actually a grand illusion? What if everything we see and experience is nothing more than a spectacularly detailed projection, like a cosmic movie screen? This brings us to one of the most astonishing theories to emerge from the study of black holes and quantum gravity, the holographic principle, and its profound implications for the nature of quantum fluctuations themselves. The story of the holographic principle begins not with the beginning of the universe, but with the end of things, specifically with the thermodynamics of black holes. In the 1970s, physicist Jacob Bekenstein made a startling proposal. He argued that a black hole's event horizon, the point of no return, must have entropy. This was a bizarre idea because entropy is a measure of information, of the number of ways a system's microscopic parts can be arranged. But a black hole, according to classical general relativity, is the simplest object imaginable. It can be completely described by just three numbers: its mass, its electric charge, and its spin. It was a profound puzzle. How could an object that is supposedly featureless and simple have a huge amount of entropy, which implies complexity and information? Stephen Hawking later confirmed this by showing that a black hole's entropy is proportional to the area of its event horizon, not its volume. This was the first hint that the information content of a region of space might be encoded on its boundary, not within its volume. This idea was pushed into entirely new territory in the 1990s by physicists like Gerard T. Hooft and Leonard Susskind. They took the black hole entropy result and asked a breathtaking question. If the maximum amount of information you can pack into any region of space is limited by the area of its surface, not by the volume inside, what does that say about reality itself? It suggests that a three-dimensional volume of space can be completely described by a theory that lives on its two-dimensional boundary. All the information about every star, every planet, every person, and every quantum fluctuation happening inside a region is somehow painted onto the surface area enclosing that region. Our rich three-dimensional reality is in effect a holographic projection of that two-dimensional data. The world we experience is like a magnificent, immersive 3D movie that is being projected from a flat 2D screen. So what does this mean for the quantum fluctuations we've been discussing? If the holographic principle is true, then those fluctuations aren't truly happening within the space we perceive. The seething quantum foam, the virtual particles popping in and out of existence, these are not the fundamental process. They are the projected effect. The real, fundamental physics, the actual data processing and information shuffling, is happening on the distant, two-dimensional boundary of the universe. The fluctuations we measure are a translation, a decoding of information that is being updated and processed on that cosmic film. It would be like watching the pixels on your television screen flicker and change. The story isn't happening inside the television. It's being broadcast from a remote source, and the screen is just the interface. In the holographic universe, the entire cosmos is that screen, and the quantum fluctuations are the static and noise of the projection itself. This radically changes our perspective on problems like the cosmological constant. The catastrophic discrepancy in the energy of the vacuum might be a misunderstanding stemming from our incorrect belief that reality is fundamentally three-dimensional. We are trying to add up all the quantum fluctuations in the volume of space, but if the true degrees of freedom lie on the boundary, our calculation is fundamentally flawed. The holographic principle could provide a natural way to explain why the observed vacuum energy is so small. The true number of independent variables in the universe is vastly smaller than what a standard quantum field theory in 3 dimensions would predict. It offers a potential pathway to resolving the greatest mismatch in all of physics by telling us we've been counting the ingredients for the recipe all wrong. While the holographic principle remains a conjectural framework, it is supported by sophisticated mathematical work in string theory, particularly through the discovery of the anti-de Sitter/conformal field theory correspondence, or ADS/CFT. This is a concrete mathematical duality that shows a gravitational theory in a certain type of warped 5-dimensional space is completely equivalent to a quantum field theory without gravity living on its 4-dimensional boundary. It's a full realization of the holographic idea in a specific, though perhaps not our actual, universe. It provides a powerful mathematical toolkit for exploring the implications of holography, suggesting that this is far more than just a metaphor. It might be a genuine feature of how quantum mechanics and gravity are inextricably linked. The implications are staggering. It suggests that time and space are not fundamental building blocks of the universe but are emergent properties, concepts that arise from a deeper, more abstract layer of information processing. The quantum fluctuations that gave rise to galaxies and that may determine the fate of dark energy are not the engine of reality. They are the exhaust, the visible smoke from a fire burning on the edge of the cosmos. It is a theory that humbles our place in the universe, not by making us small, but by suggesting that everything we hold as concrete and real is a magnificent and incredibly persistent illusion. But if the very fabric of reality might be an emergent projection, a grand cosmic illusion, could something as intimate and immediate as our own consciousness also be woven from these quantum threads? This brings us to one of the most speculative and controversial frontiers of all, a theory that attempts to bridge the gap between the mind and the cosmos by suggesting that the phenomenon of consciousness itself might be intimately connected to the quantum fluctuations occurring within our own brain. The conventional, mainstream view in neuroscience is that the brain is a classical system. Consciousness in this model is an emergent property of the complex computation performed by its billions of neurons firing in intricate networks. It's a view that treats the brain like an extraordinarily sophisticated computer, where signals travel along well-defined pathways and thoughts are the output of this biological processing. This approach has been immensely successful in mapping brain regions to functions, but it struggles mightily with what philosophers call the hard problem of consciousness. Why should all this electrical and chemical activity produce a subjective, inner experience at all? Why do we feel anything? The sensation of the color red, the taste of chocolate, the ache of sadness, these qualitative experiences seem to defy explanation in purely mechanistic terms. This gap has led a small but dedicated group of physicists and theorists to propose a radically different idea. Perhaps the brain is not a classical computer but a quantum one. The most famous of these proposals is the orchestrated objective reduction theory, or ORCH, put forward by renowned physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff. Their theory is a breathtaking synthesis of two profound mysteries, the nature of consciousness and the unresolved quantum to classical transition. Penrose and Hameroff start with a striking observation. General anesthesia reliably switches off consciousness without killing the patient or causing massive brain damage. How does it work? The drugs used are often non-polar molecules that seem to target structures inside the brain's neurons called microtubules. These microtubules are part of the cell's skeleton, a scaffolding of proteins that gives the cell its shape and helps transport materials. Hameroff proposed that these microtubules are more than just structural, they could be the brain's quantum computing components. Their precise, lattice-like structure might be able to shield quantum states from the noisy, warm, wet environment of the brain, an environment that physicists have traditionally argued would destroy any fragile quantum coherence almost instantly. This is where Penrose's contribution becomes crucial. He had previously argued that the transition from a fuzzy, probabilistic quantum state to a definite, classical state, a process called wave function collapse, is not random as in standard quantum theory, but is instead a gravitational effect. In his view, when a quantum system becomes too massive or too separated in spacetime, its own gravity forces it to choose one definite state. This moment of objective collapse, Penrose theorized, is not just a physical event. Each collapse is a moment of proto-consciousness, a single, tiny bit of experience. In the ORCH model, the microtubules inside neurons are where these quantum computations are happening. They are processing information in superpositions of states, and when a gravitational threshold is reached, they collapse into a definite state. According to the theory, this collapse isn't just a calculation, it is a moment of conscious awareness. The orchestration of these collapses across vast networks of microtubules is what gives rise to our stream of conscious thought. And what drives these quantum superpositions in the first place? The theory points directly to the quantum vacuum. The constant fluctuations, the seething energy of spacetime itself at the Planck scale, could be providing the background noise or the trigger for these quantum processes within the microtubules. In this view, our consciousness isn't just locked inside our skulls. It is a dynamic interplay between the neurobiology of our brains and the fundamental quantum fluctuations of the universe. It is vital to understand that this theory remains highly controversial and is rejected by the majority of physicists and neuroscientists. The criticisms are significant. The brain is simply too warm, too wet, and too chaotic. Quantum states are incredibly delicate and are thought to decohere, to lose their quantum magic in a fraction of a second in such an environment, far too quickly to play any meaningful role in neural processes. Critics argue that classical explanations of neural network complexity are sufficient, and that introducing quantum mechanics is an unnecessary complication, a case of what's sometimes dismissively called quantum mysticism. Yet the theory persists, fueled by the profound difficulty of the hard problem. It represents a daring attempt to find a place for mind within matter, not as a passive byproduct, but as an active participant rooted in the most fundamental level of physics. It suggests that the inner light of consciousness and the outer darkness of the quantum vacuum might not be separate realms, but deeply connected aspects of a single, mysterious reality. Whether ORCH or a similar quantum consciousness theory ever gains widespread acceptance, it forces a fascinating question. If the universe is indeed built on a foundation of unpredictable fluctuation, is it so strange to think that the most unpredictable thing we know, our own conscious experience, might somehow be tapping into that same primordial source? But this journey into quantum consciousness and the very structure of reality forces us to confront a much older and more fundamental mystery, one that lies at the absolute heart of quantum mechanics itself. It's a puzzle so deep that physicists have been arguing about it for nearly a century, and it asks a seemingly simple question: what happens when we try to measure something? This is the infamous measurement problem, and it's here that we find one of the most intriguing roles for quantum fluctuations, not as a creative force or a driver of cosmic fate, but as a potential trigger for the very act of reality itself. To understand the measurement problem, we need to rewind to the early 20th century and the birth of quantum theory. Scientists discovered that particles like electrons don't behave like tiny billiard balls. Instead, they are described by a mathematical entity called a wave function. This wave function doesn't tell you where the particle is. It tells you the probability of finding it in any given location if you were to look. Before a measurement, according to the standard interpretation, the particle isn't in one place or another. It exists in a blurry superposition of all possible positions, a ghostly haze of potentiality. It's only at the moment you make a measurement, the moment you observe it, that this wave function seems to violently collapse and the particle snaps into a single, definite location. The act of looking itself appears to force the universe to make a choice. This is, to put it mildly, deeply weird. Why should observation have such a special, powerful role? What exactly counts as a measurement? Is it a conscious human observer, a machine, a single atom bumping into another? The theory provides a beautiful mathematical description of what happens before and after the collapse, but it is completely silent on the mechanism of the collapse itself. This is the measurement problem, the jarring, unexplained gap between the fuzzy world of quantum possibilities and the sharp, definite world we actually experience. This is where quantum fluctuations enter the story as a potential physical solution. One prominent idea, known as spontaneous collapse theory, suggests that wave function collapse isn't triggered by observation at all, but happens spontaneously and randomly due to a fundamental, underlying noise in the universe. The most developed version of this idea is called continuous spontaneous localization, or CSL. In this model, the wave function of a particle is constantly being jostled by a very weak background field of randomness. For a single, tiny particle like an electron, this jostling is so faint that its wave function can remain in a superposition for a long time. But for a larger object, something made of billions of trillions of atoms, the effect of all these tiny, random kicks adds up. The superposition becomes unstable and rapidly collapses into a single state. In this view, a measurement is just an interaction that amplifies this effect, making the collapse inevitable. And what could be the source of this universal background noise? The prime candidate is the very quantum foam we've been discussing, the seething sea of zero-point energy fluctuations. The spacetime foam, with its constant churn of virtual particles and energy, could provide the perfect source of randomness to gently, continuously nudge wave functions toward a definite state. It would mean that the transition from quantum to classical isn't a mysterious philosophical event, but a physical process, like a pencil balancing on its tip that is eventually knocked over by the constant, microscopic vibrations in the air around it. The larger the object, the more susceptible it is to being knocked into a definite state by this universal background hum. This offers a compelling way to demystify the role of the observer. In the CSL model, you don't need a conscious mind to collapse a wave function. The collapse happens naturally due to the object's size and its inevitable interaction with the fluctuating quantum vacuum. A single electron can be in two places at once because it's too small to be significantly disturbed by the background noise. But a cat or a measuring instrument or a human being is far too large and complex. Their wave functions collapse almost instantly. This would explain why we never see macroscopic objects in superpositions. The universe itself is constantly measuring them through the gentle, unceasing pressure of quantum fluctuations. Of course, this is still a speculative theory. The hypothesized collapse field has never been directly detected, and experiments are ongoing to test its predictions by trying to create larger and larger objects in a state of quantum superposition to see if they collapse sooner than standard quantum theory would predict. But whether CSL is ultimately correct or not, it represents a powerful attempt to ground one of the most philosophical problems in physics in a tangible, physical process, connecting the enigma of measurement directly to the hidden, energetic simmer of empty space. It suggests that the definite world we experience isn't a paradox, but a consequence of our size, and that the quantum weirdness never truly goes away. It's just constantly being washed out by the silent, invisible storm of fluctuations that fills the void. This profound debate between determinism and free will, sharpened by the lens of quantum mechanics, leads us directly into one of the most personal and philosophically charged theories on our list. If the universe operates on a foundation of pure randomness at the quantum level, does that randomness offer a chink in the armor of a predetermined cosmos, a tiny opening through which genuine free will might emerge? This is the tantalizing possibility that theorists have explored for decades, weaving together physics, philosophy, and neuroscience in a search for the origins of human choice. For centuries, the Newtonian view of the universe suggested a clockwork reality. If you knew the precise position and momentum of every particle, the argument went, you could, in principle, calculate the entire future and rewind the entire past. This is Laplace's demon, the idea of a perfect intelligence for whom the future is entirely fixed. In such a deterministic universe, free will is an illusion. Your thoughts, your decisions, and your actions would simply be the inevitable outcome of a vast, complex chain of cause and effect stretching back to the Big Bang. You feel like you're making choices, but those feelings are themselves the predetermined results of prior physical states. This is a deeply unsettling conclusion for many, as it seems to reduce human consciousness to a passive passenger in a machine running on a set of immutable rails. The discovery of quantum mechanics in the early 20th century appeared for a time to throw a wrench into this deterministic machine, At the subatomic level, outcomes are not predetermined. An radioactive atom decays at an exact moment that is fundamentally unpredictable. Which path a photon takes in a double-slit experiment is a matter of probability, not certainty. This inherent indeterminacy, this fundamental randomness, seemed to break the chain of strict cause and effect. For some philosophers and scientists, this was the opening they were looking for. Perhaps this quantum randomness does not just introduce chance into the universe, perhaps it provides the raw material for free will. The idea is that the human brain, a vastly complex biological system, could somehow harness or amplify these quantum uncertainties. A single random event at the neuronal level triggered by a quantum fluctuation could be the seed that tips the scales between one decision and another, allowing for a genuinely free choice that was not preordained by the state of the universe a moment before. This view, often called libertarian free will, suggests that our minds are not completely subject to the deterministic laws of physics because those very laws contain an element of indeterminacy. The physicist Roger Penrose, whom we discussed regarding consciousness, is a prominent proponent of this idea, arguing that non-computable quantum gravitational processes in the brain could allow for decisions that are neither random nor determined but truly free. In this model, you are not a clockwork automaton, nor are you a slave to cosmic chance. Instead, your conscious self could be an active participant, somehow guiding or selecting from a menu of quantum possibilities to make a meaningful choice. However, this proposal faces massive and compelling criticisms from both physicists and philosophers. The most common objection is that swapping determinism for randomness doesn't actually get us to free will. It just replaces a puppet on a string with a puppet on a random number generator. If your decision to, say, drink tea instead of coffee is the result of a random quantum event in your brain, is that really a free choice, or is it just a flip of a cosmic coin over which you have no control? True free will seems to require not randomness but agency, the ability to consciously control the outcome. Introducing quantum randomness seems to undermine control rather than enhance it. Furthermore, there's the immense practical challenge of the brain's environment. As we touched on earlier, the brain is a warm, wet, and noisy place. Most physicists argue that any fragile quantum coherence would be destroyed almost instantly by its surroundings, a process called decoherence. For quantum effects to play a meaningful role in decision-making, they would need to be isolated long enough to influence neural processes, and there is currently no widely accepted evidence that this occurs. The majority of neuroscientists maintain that the brain operates classically, with decisions emerging from the complex but ultimately deterministic firing of neurons. This leaves us with a fascinating and unresolved tension. The deterministic view preserves the laws of physics as we understand them at the macro scale but can feel existentially bleak. The quantum free will view offers a more appealing narrative of human agency but struggles with scientific plausibility and the problem of equating freedom with randomness. Some thinkers have tried to find a middle path, suggesting that perhaps we need a more sophisticated understanding of what free will means. Compatibilism, for instance, is the philosophical position that determinism and free will are not actually mutually exclusive. It argues that free will is about acting according to one's own desires, motivations, and character, even if those elements are themselves the product of prior causes. In this view, you are free if you can do what you want to do, regardless of whether the wanting itself was predetermined. The question of whether quantum fluctuations provide a physical basis for free will remains one of the most hotly debated topics across science and philosophy. It forces us to confront the deepest questions about what it means to be a conscious agent in a physical universe. While the current scientific consensus leans heavily against the idea, the mystery is far from solved. The intersection of quantum physics, neuroscience, and philosophy continues to be a fertile ground for speculation, reminding us that some of the most profound mysteries are not just out in the cosmos, but are woven into the very fabric of our own minds and the choices we make every single day. And this very randomness that challenges our notions of free will pushes us toward one of the most staggering and mind-expanding theories in all of physics, a concept that suggests that every flicker of quantum potential doesn't just collapse into a single reality, but instead blossoms into an entire universe of its own. This is the many worlds interpretation of quantum mechanics, a vision of reality where the cosmos is constantly branching, creating a multiverse so vast that every possible outcome of every quantum event is realized somewhere. The story begins in the 1950s with a young physicist named Hugh Everett III. He was deeply troubled by the unresolved paradox at the heart of quantum mechanics, the measurement problem. He found the idea of a mysterious, instantaneous wave function collapse to be philosophically unsatisfying and mathematically inelegant. So he proposed a radical alternative. What if the wave function never collapses at all? What if every single possible outcome contained within that probabilistic haze actually happens? Everett's revolutionary idea was that the universe is described by a single, never-collapsing wave function that relentlessly evolves according to the Schrödinger equation, a deterministic law of physics. In this view, the apparent collapse is an illusion of our perspective. When a quantum event with multiple possible outcomes occurs, like an electron being measured in one of two positions, the entire universe doesn't choose one path. Instead, it splits or branches into multiple copies. In one new universe, the electron is measured here. In another, nearly identical universe, it is measured there. The observer themselves splits along with the experiment, each copy believing, quite correctly from their point of view, that their outcome was the one that occurred. In the many worlds view, those quantum fluctuations we've been discussing aren't just momentary blips. They are the engines of creation, constantly spawning new parallel realities. Every time a virtual particle pair pops into existence, the universe might branch into one reality where it appears and another where it doesn't. Every random atomic decay, every photon's path chosen, every tiny fluctuation is a potential branch point. The result is a truly unimaginable multiverse, a foaming ocean of universes where every conceivable history plays out. There's a universe where you decided to wear a blue shirt today instead of a black one. There's a universe where the dinosaurs were never wiped out by an asteroid. There's a universe where every possible variation of physical laws and constants exists. This isn't science fiction. For proponents of many worlds, this is the straightforward, non-magical interpretation of the mathematics we already have. This idea solves the measurement problem with breathtaking elegance by simply eliminating the need for a collapse. There is no special role for the observer, no mysterious transition from the quantum to the classical. There is just reality in all its possible permutations existing simultaneously. The reason we only experience one outcome is not because the others vanish, but because our conscious awareness becomes entangled with one specific branch of the universal wave function. We are like a person floating down a massive branching river. At each fork, we can only follow one current, utterly unaware of the other streams flowing alongside us, even though they are just as real. The implications of this are, of course, utterly profound. It suggests that all possibilities are realized. Every tragedy averted in our world happens in another. Every missed opportunity is seized in a neighboring reality. Every historical event that could have unfolded differently did. The multiverse becomes a tapestry of infinite variation, woven from the threads of quantum probability. Critics often argue that this is an extravagant, unfalsifiable hypothesis, that it violates Occam's razor by multiplying entities beyond necessity. Proponents counter that it is actually the most parsimonious interpretation because it requires no extra physics, no collapse postulate, no new laws. It only requires that we take the wave function and its evolution seriously and accept the logical consequence of that mathematics. which is a reality far grander and stranger than we ever imagined. Whether this infinite branching tree of universes is the true nature of reality remains one of the most exciting and open questions at the frontier of physics, a stunning possibility that places every quantum fluctuation at the very center of a cosmic story of endless creation. But this breathtaking vision of parallel universes branching from every quantum event forces us to ask a crucial question about our own specific reality. Out of the infinite possibilities, why does our universe look and behave the way it does? Why do we have the specific set of fundamental forces and the overwhelming dominance of matter that makes our existence possible? The answer to this profound mystery may lie in another critical role of quantum fluctuations, one that shaped the very laws of physics in the first instance after the Big Bang through a process known as spontaneous symmetry breaking. To grasp this idea, we first need to understand what physicists mean by symmetry. In this context, it doesn't refer to a pretty shape. It describes a kind of sameness or invariance under change. Imagine a perfectly round, featureless sphere. It looks the same no matter how you rotate it. It possesses a high degree of rotational symmetry. Now, picture that sphere cooling and developing a single, distinct north pole. Suddenly, that perfect symmetry is broken. The sphere now has a specific orientation. This transition from a uniform, symmetric state to a more complex, asymmetric one is the essence of spontaneous symmetry breaking, and it's a process that defines how our universe cooled from an unimaginably hot, dense state. In the first fraction of a second after the Big Bang, the cosmos was a seething, ultra-energetic soup where the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were merged into a single, unified superforce. There was no distinction between them. As the universe expanded and cooled, it underwent a series of dramatic phase transitions, much like steam condensing into water or water freezing into ice. At each critical temperature threshold, the underlying quantum fields that permeate all of reality settled into new, more stable states. This settling process is spontaneous symmetry breaking. The perfectly symmetric, unified force fractured into the distinct forces we observe today. The Higgs field, which gives particles their mass, is a prime example of this. In the early hot universe, the Higgs field had a value of 0 everywhere, symmetric and silent. As the cosmos cooled, it spontaneously chose a new, non-zero value everywhere, breaking that symmetry and instantly endowing many elementary particles with mass. But here's where quantum fluctuations become the ultimate cosmic choreographers. These phase transitions were not perfectly smooth and uniform. The chaotic jitter of the quantum vacuum, the same foam we've discussed, introduced tiny, random imperfections into the process. Think of it like water freezing on a pond. It doesn't freeze into a perfect, single crystal all at once. Instead, ice crystals form randomly at different points and then grow until they merge, creating a patchwork of domains with slightly different orientations. In exactly the same way as the universe cooled and its symmetries broke, quantum fluctuations caused different regions of space to choose their new ground state in slightly different ways. These domain walls, cosmic strings, and other potential defects are fossilized remnants of those random choices, and their gravitational effects are something astronomers actively search for in the cosmos today. This process of symmetry breaking, guided by quantum randomness, didn't just create the forces, it might also be the reason we exist at all. One of the greatest puzzles in cosmology is the matter-antimatter asymmetry. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. Since these two opposites annihilate on contact, such a universe would have quickly devolved into a lifeless sea of pure radiation. Yet here we are in a universe made almost entirely of matter. For every billion photons of light in the cosmos, there is roughly one proton, one bit of matter that somehow survived the Great Annihilation. This implies that for every billion pairs of matter and antimatter particles created, one extra matter particle was left over. How did this happen? The solution proposed by physicist Andrei Sakharov requires three conditions to be met, and spontaneous symmetry breaking plays a starring role. The laws of physics must behave slightly differently for matter and antimatter, a phenomenon called CP violation. The universe must have been out of thermal equilibrium, which those rapid phase transitions provided. And there must be processes that change the net number of matter particles. Theories like leptogenesis suggest that the heavy, hypothetical particles responsible for the early force unification decayed asymmetrically, thanks to CP violation, producing a tiny excess of matter over antimatter. And what triggered these decays and set the conditions for this asymmetry? The random nudges of quantum fluctuations during the moment of symmetry breaking. In this view, the entire visible universe, every star, every planet, every one of us is the result of that 1 in a billion imbalance, a statistical fluke amplified from the quantum noise of the infant cosmos. We are not just the children of quantum fluctuations, we are the children of a specific, fortunate fluctuation that broke the symmetry in just the right way to leave a universe filled with something rather than nothing. But if spontaneous symmetry breaking and quantum fluctuations set the initial conditions for our universe, how do we actually interact with and control this chaotic quantum world in the here and now? This brings us to a truly bizarre and counterintuitive phenomenon that turns the very act of observation into a tool of creation and preservation. It's called the quantum Zeno effect, and it suggests that by simply watching something closely enough, we can effectively freeze it in time, suppressing the natural dance of quantum fluctuations to hold a particle in a single state. The name itself is a playful nod to the ancient Greek philosopher Zeno of Elea, who famously proposed a series of paradoxes arguing that motion is an illusion. One of these, the arrow paradox, claims that at any given instant, a flying arrow is motionless in a specific place. Because time is composed of such instants, Zeno argued, the arrow must be stationary at all times and therefore cannot actually be moving. While this is a logical fallacy in the classical world, in the quantum realm, something strikingly similar can actually occur. The quantum Zeno effect proposes that the continuous, rapid measurement of a quantum system can prevent it from evolving, effectively freezing it in its initial state. It's as if you could stop a pot of water from boiling by staring at it intently enough. The mechanism hinges on the peculiar nature of wave function collapse. Imagine an unstable quantum particle, like an atom in an excited energy state that is likely to decay by emitting a photon. Left to its own devices, influenced by the jostling of quantum fluctuations, its wave function will gradually evolve, increasing the probability that it will be found in the decayed state. Now, what happens if we repeatedly measure it, constantly asking, "Are you still in the excited state?" Each time we measure it and find it still excited, we collapse its wave function back to that definite starting point. This act of measurement resets the evolutionary clock. If the measurements are rapid enough, faster than the natural timescale of the quantum system's evolution, the particle simply doesn't have time to transition. It gets stuck like a student constantly interrupted while trying to complete their homework. This isn't just a theoretical curiosity, it has been demonstrated in the lab. One of the clearest examples came in 1990, when a team at the National Institute of Standards and Technology, NIST, led by David Wineland, used laser pulses to repeatedly measure the quantum state of beryllium ions. By frequently observing whether the ions were in one energy state or another, they were able to dramatically slow down the rate at which the ions transitioned between those states. The more frequently they made their measurements, the more effectively they suppressed the natural quantum evolution. They had harnessed the power of observation to control the quantum world. The implications for this are profound, especially in the quest to build practical quantum computers. One of the biggest challenges in quantum computing is decoherence. the process where a fragile quantum state or qubit loses its information by interacting with its environment. This interaction is essentially an inadvertent, continuous measurement by the outside world, causing the qubit to collapse from its useful superposition into a boring classical state. The quantum Zeno effect offers a potential strategy to fight this. By proactively and carefully measuring the qubits in a specific way, we could potentially freeze them in their desired states, protecting the encoded information from the disruptive influence of external quantum fluctuations long enough to perform computations. It's a fascinating paradox, using measurement, the very thing that usually causes collapse, as a shield to prevent unwanted collapse from the environment. Beyond technology, the effect forces us to confront the deep and strange relationship between reality and information. It suggests that information gain, the act of learning something about a system, is not a passive process but an active intervention that physically alters the system's destiny. In the quantum world, to know something is to change it, and in the case of the quantum Zeno effect, to know it repeatedly is to hold it still. This gives the quantum vacuum and its fluctuations a new role, not just as a source of noise and decay, but as a medium that can be mastered and quieted through intelligent observation, allowing us to carve out islands of stability in the seething quantum foam. Yet for all their potential role in cosmic history and fundamental physics, could these quantum fluctuations also be acting on a scale far closer to home, subtly influencing the very blueprint of life itself? This brings us to a fascinating and highly speculative frontier where quantum biology meets evolutionary theory, investigating the provocative idea that random quantum events within DNA might occasionally accelerate mutation rates, potentially nudging evolution along pathways that pure chance alone cannot explain. The standard model of evolutionary biology is a powerful and profoundly successful framework built on a classical foundation. In this view, mutations, the raw material for natural selection, are random errors. They occur due to external factors like ultraviolet radiation from the sun or internal chemical accidents during the careful process of DNA replication. These copying mistakes are then either beneficial, harmful, or neutral, and over immense spans of time, beneficial mutations are gradually selected for, leading to the breathtaking diversity of life we see today. This process is undirected and statistical, a grand game of chance played out over billions of generations. It requires no mystical forces or hidden quantum hand. Classical thermodynamics and chemistry seem more than sufficient to account for the errors that drive genetic change. However, a small group of scientists and theorists have begun to ask a daring question. What if the story isn't entirely classical? DNA, the molecule that holds our genetic code, is incredibly small, operating at the nanoscale. At this level, the bizarre rules of quantum mechanics begin to take precedence over the familiar laws of classical physics. The atoms within a DNA strand are constantly vibrating, and the protons that form the hydrogen bonds between the base pairs, the famous rungs of the double helix ladder, can, in theory, behave as quantum particles. This opens the door to a remarkable possibility, the phenomenon of quantum tunneling. Quantum tunneling is a well-established effect in physics where a particle can, in a sense, disappear through an energy barrier that it classically shouldn't be able to overcome. Imagine rolling a ball up a hill. If you don't give it enough energy to reach the top, it will roll back down. In the quantum world, there's a small but real probability that the ball could simply appear on the other side of the hill without ever having gone over it. It's as if it tunneled through. In the context of DNA, this tunneling could apply to protons. The protons that link the two strands of the helix can potentially tunnel from their standard position to an alternative location, creating a temporary alternative structure for the base pair. These altered states are called tautomers. Normally, these tautomeric forms are unstable and quickly revert back. But if a DNA polymerase enzyme, the molecular machine that copies DNA, comes along and reads the strand while the proton is in the wrong place, it could copy the base incorrectly, inserting the wrong partner and creating a point mutation. The crucial point is that this mutation mechanism, driven by quantum tunneling, would be fundamentally different from a classical chemical error. It wouldn't be caused by a random thermal jostle that gives a particle enough energy to jump the barrier. It would be a truly probabilistic quantum event. The proton isn't jumping, it's tunneling, an act that is inherently unpredictable and instantaneous. This means the mutation rate from such a process could, in theory, operate on a different timescale or be influenced by factors that don't affect classical mutation rates. It would introduce a source of genetic randomness that is rooted in the fundamental indeterminacy of the quantum world. The evidence for this remains tentative and is the subject of intense debate. Some laboratory studies have suggested that proton tunneling could indeed play a role in certain types of mutations, particularly those involving the bases guanine and cytosine. Other researchers argue that the warm, wet, and chaotic environment of the cell would rapidly destroy any fragile quantum coherence, a process called decoherence, making sustained quantum effects like tunneling for mutation highly unlikely. They maintain that classical processes are more than enough to explain observed mutation rates. Yet, the idea is compelling because it offers a potential mechanism for a long-standing puzzle in evolution: the apparent speed and creativity of the process. While natural selection is powerful, it can only work with the variation it is given. If mutations were purely classical and random, some theorists wonder if there would have been enough time for the incredible complexity of life to evolve. Could quantum tunneling provide a subtle, additional source of genetic variation, occasionally offering up beneficial mutations a little faster than a purely classical process would allow? It wouldn't guide evolution or make it purposeful. The mutations would still be random, but it might make the lottery of life run on a slightly different, quantum-influenced schedule. This speculative bridge between the quantum vacuum and the diversity of life suggests that the same fundamental unpredictability that shapes the cosmos might also be whispering ever so faintly in the very genes of every living thing. This idea of a fundamental randomness woven into the fabric of life brings us to a theory that stands as a profound philosophical counterpoint, a concept that suggests our universe's specific quantum rules are not a random accident, but a necessity for observers like us to even be here to ponder them. This is the anthropic principle, and it applies a startling lens to the question of why our quantum vacuum has the exact, seemingly fine-tuned properties it does. Properties that made the emergence of galaxies, planets, and life not just possible, but perhaps inevitable. The core of the anthropic principle is deceptively simple. The observed values of physical constants and laws are not arbitrary. They must be compatible with the existence of conscious life that can observe them. We do not observe a universe with, for instance, a cosmological constant 120 orders of magnitude larger, because such a universe would have blown itself apart in a fraction of a second, leaving no one behind to measure it. It's a selection effect on a cosmic scale. We find ourselves in a universe that permits our existence simply because we couldn't find ourselves in one that doesn't. This isn't an explanation in the traditional sense. It doesn't tell us why the constants have their values, but it provides a powerful framework for understanding why certain seemingly miraculous coincidences aren't so miraculous after all. Now apply this reasoning directly to the quantum fluctuations we've been exploring. Their specific character is not a given. It is dictated by the underlying laws of physics and the values of fundamental constants like the strength of the electromagnetic force or the mass of the electron. Imagine if the amplitude of those primordial quantum jitters had been significantly smaller. When inflation stretched them, they would have created only the faintest of density variations. The gravitational pull of these regions would have been too weak to overcome the expansion of the universe, and matter would never have clumped together to form the first stars and galaxies. Our universe would be a vast, dark, and utterly empty void. Conversely, if the fluctuations had been much larger, the density contrasts would have been extreme. Matter would have collapsed too rapidly, forming enormous black holes and chaotic structures long before stable solar systems or life-supporting planets could ever arise. In either scenario, we wouldn't be here. The anthropic principle reframes this breathtaking fine-tuning. It suggests that within a vast multiverse, perhaps the one predicted by the many worlds interpretation or by the eternal inflation scenario, every possible value for the fluctuation amplitude and every possible set of physical laws is realized in some separate universe. The vast majority of these universes are stillborn or barren, but in an infinitesimally small subset, the dice roll just right, the quantum noise is at the perfect volume, and the conditions for life emerge. We, of course, find ourselves in one of those rare Goldilocks universes. From this perspective, the specific nature of our quantum fluctuations isn't a lucky break. It's a cosmic prerequisite for our own existence. We are not witnessing a universe fine-tuned for life. We are life that has emerged in a universe with the specific tuning that allows it. This line of thinking offers a potential, albeit controversial, way to approach the cosmological constant problem. The staggering discrepancy between the predicted and observed energy of the vacuum might be resolved by the anthropic argument. If the multiverse contains a landscape of universes with every possible value of the cosmological constant, then only those with a value incredibly close to zero, like our own, can ever develop the large-scale structure necessary for life. The value isn't determined by a beautiful equation. It's an environmental accident, a random variable that had to fall within a narrow window for us to be here to measure it. This is a humbling shift in perspective. It moves the quest for explanation from discovering a unique, fundamental law to understanding the statistical distribution of properties across a possibly infinite multiverse. The answer to why this number becomes because this is one of the few numbers that allows for the question to be asked. Critics of the anthropic principle often dismiss it as a conversation stopper, a retreat from the traditional goal of physics to find deterministic causal explanations. It can feel like giving up, saying that some things are just the way they are because otherwise we wouldn't be here. Proponents, however, see it as a necessary dose of reality, a tool that helps us distinguish between problems that might have a unique physical solution and those that are ultimately questions of our own place in a much larger and perhaps untestable cosmic landscape. It doesn't negate the search for deeper theory, it simply refines the questions we ask, whether one finds it deeply satisfying or deeply unsettling. The anthropic principle forces a profound reconsideration of our place in the cosmos, suggesting that the quantum whispers we study are not just random noise, but the very specific signature of a universe that has grown aware of itself. And this search for a deeper layer of reality, where the quantum and the cosmic are one, brings us to the grandest challenge in all of physics, uniting the two most successful but seemingly incompatible theories we have. On one hand, we have quantum mechanics, which describes the bizarre, probabilistic world of the very small with breathtaking accuracy. On the other, we have Einstein's general relativity, which paints a majestic picture of gravity as the curvature of smooth, continuous spacetime, perfectly explaining the orbits of planets and the bending of light around galaxies. For decades, these two pillars have stood apart, refusing to be joined. Yet many physicists believe the very key to their unification has been hiding in plain sight all along, shimmering within the quantum foam itself. The bridge between these worlds may be built from the very fluctuations we've been exploring, suggesting that gravity itself must have a quantum origin. To understand why this is such a monumental problem, imagine trying to describe a ballet dancer using the rules of football. The languages, the scales, and the very goals are completely different. Quantum mechanics deals in probabilities, particles, and discrete packets of energy. General relativity is about deterministic curves, fields, and the seamless fabric of the cosmos. When we try to force Einstein's equations onto the quantum world, they break down catastrophically. The equations of general relativity require spacetime to be smooth and well-behaved, but the quantum vacuum is anything but. It's a turbulent sea of wildly fluctuating energy. If you try to calculate the gravitational effect of all those virtual particles popping in and out of existence, the math produces infinity's nonsensical answers that point to a fundamental flaw in our understanding. This tells us that at the very smallest scales, near the Planck length, the classical idea of a smooth spacetime must give way to something new, something quantum. This is where the concept of the graviton comes in. In the standard model of particle physics, each of the fundamental forces is carried by a force-carrying particle. Electromagnetism has the photon, the strong nuclear force has gluons, and the weak nuclear force has the W and Z bosons. For gravity to be united with these quantum forces, it too should have a messenger particle, the hypothetical graviton. Theorized to be a massless particle with a spin of 2, the graviton would mediate the gravitational force by being exchanged between objects with mass, much like photons are exchanged between charged particles. In this framework, what we perceive as the curvature of spacetime would actually be the net effect of countless graviton exchanges. And just like all other quantum fields, the gravitational field would be subject to fluctuations. Empty space would be filled with a foam of virtual gravitons flickering in and out of existence, meaning that spacetime itself would be fundamentally fuzzy and uncertain at its heart. This idea leads to a breathtaking conclusion. If the gravitational field is quantized, then the geometry of spacetime itself must be fluctuating. John Wheeler's spacetime foam is the ultimate expression of this. It proposes that at the Planck scale, the concepts of distance and duration become meaningless. The smooth landscape of general relativity transforms into a chaotic, probabilistic foam with tiny wormholes and tunnels constantly forming and dissolving. In this view, a quantum fluctuation isn't just something that happens in spacetime. It is a fluctuation of spacetime. The very stage upon which the universe plays out is dynamic and alive, bubbling with its own quantum energy. This is why unifying gravity with quantum mechanics is so difficult. We are trying to describe the actor and the stage using the same rules, and the stage itself is made of a turbulent quantum material. Several ambitious approaches are trying to build this bridge. String theory, for instance, proposes that the fundamental constituents of reality are not point-like particles but incredibly tiny, vibrating strings. The different vibrations of these strings correspond to different particles, including the graviton. In this framework, the apparent conflict is resolved because the strings smooth out the harsh mathematical infinities that plague other attempts. Another leading contender is loop quantum gravity, which takes a different path. It suggests that spacetime itself is not continuous but is woven from finite, discrete loops, a kind of fabric of woven threads of gravity. In this theory, there is a smallest possible unit of space and time, much like a pixel on a screen, which naturally prevents those disastrous infinities from arising. Both theories, in their own way, assert that the fluctuating quantum vacuum and the structure of spacetime are inextricably linked. They are not two separate things, but two different descriptions of a single, profound reality. The implications of successfully unifying these theories would be nothing short of revolutionary. It would allow us to peer logically into the first moments of the Big Bang and the singularities at the hearts of black holes, places where our current laws of physics simply give up. It could reveal whether time itself had a beginning or if the universe could have emerged from a prior state through a quantum gravitational fluctuation. It might even provide a natural, physical explanation for the value of the cosmological constant, finally solving that epic mismatch between prediction and observation. We would move from seeing the universe as a place where things happen to understanding it as a thing that is itself happening, a dynamic, evolving, and fundamentally quantum entity. The quantum fluctuations we started with are not merely a curious sideshow. They are the very heartbeat of a deeper reality, the hidden code that writes the laws of gravity and geometry into the fabric of existence. What if the key to understanding the bizarre dance of quantum fluctuations lies not in the present moment, but in a constant conversation between the future and the past? This is the radical proposition of the transactional interpretation of quantum mechanics, a theory that dares to suggest that particles flickering into existence are the direct result of waves traveling backwards in time, handshaking with waves from the future to create the reality we perceive in the present. Developed by physicist John Cramer in the 1980s, this interpretation offers a stunningly elegant, if mind-bending, alternative to the mysterious wave function collapse, and it paints a picture of the quantum vacuum that is both strangely beautiful and profoundly interconnected. To grasp this, let's revisit the classic double-slit experiment. In the standard view, an electron is fired at a barrier with two slits. Its wave function passes through both slits, interferes with itself, and creates a pattern on the detector screen. But the moment you try to measure which slit it went through, the wave function collapses and the interference pattern vanishes. The transactional interpretation offers a completely different story. In this view, when the electron is emitted, it sends out what Cramer calls an alpha wave. This is a standard quantum wave that radiates outward in all directions, forward in time, exploring all possible paths through both slits around the barrier everywhere. This alpha wave eventually reaches the various possible detection points on the final screen. Here's where it gets incredible. According to the theory, the detection event itself then sends a confirmation wave backwards in time. This wave is a perfect echo of the alpha wave, but it travels retrogradely from the future back to the past. The transaction is completed when the alpha wave from the past and the confirmation wave from the future find each other and constructively interfere, reinforcing one another. It is this handshake across time, this closed loop of negotiation between emitter and absorber, that actually creates the tangible reality of the particle and everything we measure about it. The particle isn't a thing that travels a path, it is the result of this completed transaction. The specific point on the detector screen where the transaction is finalized is determined by which confirmation wave provides the strongest, most resonant reinforcement. Now apply this breathtaking framework to the quantum fluctuations of the vacuum. Those virtual particle-antiparticle pairs that constantly pop in and out of existence are no longer just random borrow energy events. Instead, each virtual pair represents a potential transaction. An alpha wave for an electron is emitted, and a corresponding alpha wave for a positron is also emitted. These waves travel forward, and if they can find a suitable confirmation wave from a potential absorber in the future that allows the transaction to be completed, the particles briefly become real. But in the vacuum, most of these transactions are never fully reinforced. The confirmation waves are weak or don't perfectly match, so the transaction is only partially completed, manifesting as the fleeting, ghostly existence of a virtual pair that almost instantly annihilates and returns the energy. The quantum foam, in this view, is a seething cauldron of trillions of half-finished transactions, of offers sent out and confirmations that never quite fully connect. This interpretation completely eliminates the need for a separate, mysterious wave function collapse. The collapse is the transaction. It also provides a fascinating physical picture for some of the weirdest phenomena in quantum mechanics. Quantum entanglement, for instance, where two particles remain connected across vast distances, can be seen as a single, unified transaction involving both particles. The alpha and confirmation waves tying them together simply don't care about the spatial separation between them, creating that famous, spooky action at a distance that so troubled Einstein. Perhaps the most profound implication of this view is its suggestion of a block universe, where past, present, and future all exist simultaneously in a static four-dimensional structure. The transactional handshakes are just fixed loops within this structure. This can feel deeply unsettling, as it seems to imply a predetermined universe without free will. However, proponents argue that the transactions are not predetermined in a classical sense. They are probabilistic and depend on the availability of absorbers, offering a new kind of quantum openness. The transactional interpretation doesn't answer all the questions, but it reframes them in a way that is remarkably clear and paradox-free, presenting a cosmos where the quantum vacuum's fluctuations are not mere noise, but the echoes of a continuous, universe-wide dialogue across time itself. But if the very flow of time we take for granted might be a grand cosmic illusion, it forces us to ask the most fundamental question of all: where does time itself come from? Why does it seem to flow in one direction? And could this entire experience be a consequence of the same quantum chaos we've been exploring? This brings us to one of the most profound and radical ideas on our list: the possibility that time itself is not a fundamental ingredient of the universe, but an emergent property that arises from the ceaseless churn of quantum fluctuations at the very deepest level of reality. To even begin to grapple with this, we need to step back and consider the strange status of time in our two most successful theories of physics. In Einstein's general relativity, time is woven into a four-dimensional fabric called spacetime. It is smooth, continuous, and treated mathematically on an equal footing with the three dimensions of space. You can move forward and backward in space, but the equations don't privilege one direction of time over the other. The laws work just as well if time were to run backwards. Yet our everyday experience screams otherwise. We remember the past, not the future. We age. We see cause precede effect. This is the arrow of time, and its origin is one of the greatest unsolved puzzles in physics. Quantum mechanics adds another layer of mystery. The standard Schrödinger equation that governs the evolution of quantum states is also time-symmetric. But the act of measurement, the infamous wave function collapse, seems to introduce an irreversible moment, a point of no return that introduces a clear before and after. So where does this directionality, this flow, actually come from? Many physicists now believe the answer lies in the low-entropy initial conditions of the Big Bang, as we discussed. But that just pushes the question back a step. Why did the universe begin in such an incredibly ordered, low-entropy state? This is where quantum fluctuations enter the stage, not as a side effect, but as the potential main actor. The theory of cosmic inflation suggests that a tiny, random quantum fluctuation in a pre-existing primordial field could have been the trigger for the Big Bang itself. This fluctuation, stretched and magnified by inflation, didn't just create the seeds for galaxies, it also created the conditions for time as we know it. In this view, the arrow of time is a historical accident, a fossilized remnant of that one specific fluctuation that broke the symmetry and set the universe on an irreversible path toward higher entropy. Time's arrow is not written into the fundamental laws. It is an emergent property, a story that began with a single, random event in the quantum foam. This line of thinking leads to an even more radical proposal from some corners of theoretical physics, particularly from those working on quantum gravity. In approaches like loop quantum gravity or certain interpretations of string theory, the fundamental description of reality might not include time at all. The most basic equations could be timeless, describing a static network of relationships. In this timeless picture, what we perceive as the flow of time emerges from the way these fundamental building blocks interact and change relative to each other. It's analogous to watching a movie. The film itself is a static object, a complete roll of individual frames. But when you project it at a certain speed, the illusion of motion and time emerges. In the same way, our experience of a flowing present moment could be a compelling illusion generated by the continuous evolution of quantum states. The quantum fluctuations would then be the engine of this change, the constant, random updates to the system that create the sensation of a world moving forward. This might also explain a deep property of time, why it seems to have a definite direction. The constant increase of entropy, driven by the universe's evolution from its low entropy beginning, gives us a powerful arrow. But at the quantum level, this could be linked to the way information becomes increasingly scrambled and decentralized through these fluctuations. As quantum information interacts and becomes entangled with more and more of its environment, a process called decoherence, it creates a record of the past that is practically impossible to erase. This irreversible spreading of information effectively paints the arrow of time into the fabric of reality at the microscopic level. We don't sense time flowing because of a fundamental river of time. We sense it because we are physical systems constantly interacting with an environment that is forever recording and moving into states of higher disorder, all set in motion by those initial quantum seeds. The implications of this are nothing short of worldview shattering. It suggests that the present moment, the feeling of now, is not a universal truth but a localized phenomenon, a perspective-dependent property that emerges from our interaction with the world. It means that asking what happened before the Big Bang might be as meaningless as asking what is north of the North Pole. If time itself emerged from the Big Bang, then there simply was no before in any sense we can understand. Our entire experience of reality, the past that is fixed, the future that is open, and the present that we feel so vividly, might be a beautiful and necessary consequence of the universe's quantum mechanical origins. We are not just living in time, we are living because of time, and it is the restless, fluctuating quantum vacuum that may have given us this incredible gift of a changing, evolving reality. But where does the observer truly fit into this grand cosmic scheme? Are we merely passive witnesses to a reality that unfolds on its own, or could our act of observation itself play a far more active, even fundamental, role in the very fabric of existence? This brings us to one of the most audacious and mind-bending ideas ever proposed, a theory that inverts our entire understanding of reality: John Wheeler's participatory anthropic principle. It's a concept that suggests the universe only achieves a definite reality through the act of observation, and that we, as conscious beings, are not just living in the cosmos but are essential participants in its very creation. To grasp the sheer radical nature of this idea, we need to revisit Wheeler's own journey. This was the same physicist who gave us black holes and spacetime foam, a man who was never afraid to follow a thought to its most startling conclusion. In his later years, he became utterly fascinated by the bizarre role of the observer in quantum mechanics. He devised thought experiments like the famous delayed choice experiment, which extends the classic double-slit scenario into a cosmic head trip. Imagine a particle traveling from a distant quasar, its wave function spreading out across the universe. Billions of years later, just before it's detected on Earth, an experimenter chooses whether to measure which path it took or to measure its wave-like interference pattern. Astonishingly, the experimenter's choice now seems to retroactively determine the particle's behavior billions of years in the past. It's as if the present is reaching back and influencing the past, a notion that challenges our linear perception of cause and effect at the most fundamental level. From this, Wheeler began to formulate a truly breathtaking possibility. What if the universe only comes into being through an endless series of such observations? He famously used the analogy of a game of 20 questions played with a surprising twist. You leave the room while the others choose a word. When you return, you start asking yes or no questions to guess the word. The game proceeds normally until you finally guess the word, say, cloud. But then the players reveal a secret: they hadn't chosen a word beforehand. They simply agreed to answer yes or no consistently based on your questions with no prior plan until a consistent pattern emerged from the collective answers. The word cloud wasn't predetermined, it was brought into existence by the very questions asked to define it. Wheeler suggested the universe might operate in a similar way. In the beginning, there was no pre-existing, fully formed cosmos. There was only a blurry, amorphous potentiality, a quantum fog of possibilities. Through a vast cosmic chain of observations from the first subatomic interactions to the gaze of conscious beings, the universe gradually decided on its own history and laws. The act of observation isn't just recording a pre-existing reality. It is the mechanism that actualizes it from a sea of maybes into a definite was. In this view, those quantum fluctuations aren't just random noise. They are the raw, unformed questions of the universe, and the answers provided by observers are what solidify them into the stars, planets, and physical constants we measure. This leads to the most profound implication of the participatory anthropic principle. It offers a potential, albeit highly speculative, solution to the fine-tuning problem. Why do the fundamental constants seem perfectly adjusted for life? The Wheelerian answer is that life, or at least the potential for observation, is a prerequisite for the constants to have any definite value at all. The universe couldn't have been any other way because a universe with different constants would have produced no observers to bring it into a concrete state of reality. We are not just lucky inhabitants of a Goldilocks universe. We are participators who help sing it into existence, closing a giant cosmic loop where the universe gives rise to observers, and those observers in turn give rise to the universe by defining its past. It's a vision of reality that is deeply intertwined and co-creative, where the distinction between the player and the game, the observer and the observed, finally dissolves into a single, magnificent and participatory whole. But this journey into the farthest reaches of physics and philosophy brings us back to a surprisingly tangible question, one that lies at the intersection of the quantum world and the digital age we live in. If the universe is fundamentally granular and fluctuating, how much information can it actually hold? This leads us to a fascinating theory that explores the ultimate limits of cosmic storage, suggesting that the seething energy of the quantum vacuum itself might set a hard ceiling on how much data any volume of space can contain, a concept that emerges from the brilliant fusion of quantum mechanics, general relativity, and pure information theory. To grasp this, we need to think of information not as an abstract concept but as a physical thing. In our everyday world, we measure information in bits, the fundamental units of data. A single bit can be a 0 or a 1, a switch that is off or on. In a computer, this is represented by the state of a transistor or the orientation of a magnetic domain on a hard drive. But what is the absolute physical limit of this process? What is the maximum number of bits you could possibly pack into, say, a 1-liter box? You might think the answer depends on how small you can make your switches, how tiny you can engineer your transistors. But the universe itself imposes a far more fundamental limit, and it comes from the interplay between quantum theory and gravity. The reasoning begins with a thought experiment. Imagine you want to store a single bit of information inside a small region of space. To do this, you need a particle, an electron, for instance, that can have two distinct states, like spinning up or spinning down. But to ensure that your bit is reliably stored and can be read, you have to confine that particle within your chosen region, and this is where quantum mechanics throws its first curveball. Heisenberg's uncertainty principle tells us that the more precisely you confine a particle, the more uncertain its momentum becomes. It starts jittering around with enormous energy. Essentially, the smaller the box you try to put it in, the more violently it rattles around like a hyperactive bee in a tiny jar. Now, here's where gravity enters the picture. If you keep making your box smaller and smaller to pack in more bits, the energy contained within that tiny volume becomes immense because of this quantum jitter. According to Einstein's famous equation, energy is equivalent to mass, so this concentrated energy will have a gravitational effect. If you try to pack too much information into too small a space, the energy density becomes so extreme that the entire region collapses into a black hole. And once you've made a black hole, you can't retrieve that information. It's hidden behind an event horizon. Therefore, the maximum amount of information you can store in a region is limited by the size of the smallest black hole that could contain that region. A black hole's entropy, which is a measure of its information content, is proportional to the area of its event horizon, not its volume. This was the groundbreaking insight from Jacob Bekenstein and Stephen Hawking that we touched on earlier. This leads to the holographic principle in its most general form. The maximum number of bits of information that can be stored in any region of space is not proportional to its volume, as we might intuitively guess, but to the surface area of that region, measured in Planck units. To put this in perspective, imagine a perfect, featureless sphere 1 meter in diameter. According to classical intuition, the amount of information it can hold should be related to its volume. But the holographic bound says the ultimate limit is dictated by its surface area. The number of possible states, the total information capacity, is mind-bogglingly large, roughly 10 to the power of 70 bits for a region the size of our entire observable universe, but it is nonetheless finite. And it is a limit imposed by the laws of physics themselves. So, where do quantum fluctuations fit into this cosmic data limit? They are the physical manifestation of this maximum information density. The quantum foam, with its constant churn of virtual particles, isn't just empty noise. It is the universe operating at its maximum possible information processing capacity. Think of empty space not as a blank slate, but as a hard drive that is completely full. It is constantly writing and rewriting data at the maximum speed allowed by physics. Each virtual particle pair is like a single bit flickering between 0 and 1. The fluctuations represent the fundamental, irreducible noise of a system that is saturated with information. You cannot pack any more data into a given volume because the quantum vacuum is already using every available pixel of spacetime to its absolute limit. This is why the Casimir effect occurs when you place two plates close together. You are physically restricting the number of possible wave modes, the number of available bits that can fluctuate between them, creating an imbalance with the unrestricted space outside. This has a stunning implication for our understanding of reality. It suggests that the universe might be fundamentally two-dimensional, with the three-dimensional world we experience being a projection, much like a hologram. The information needed to describe every particle, every force, and every quantum fluctuation within our cosmic horizon could be encoded on its distant boundary. The fluctuations we see and measure are not the deepest level of reality. They are the projected image of information processing happening on a distant, two-dimensional surface. This doesn't mean our reality is an illusion, but that it is emergent, much like the seemingly smooth image on a television screen emerges from the frantic activity of millions of individual pixels. The quantum foam is the grain of that cosmic screen, the finest level of detail the universe can possibly render, and it is set by the ultimate limits of information itself. But what if the very graininess of spacetime, the fundamental limit set by the Planck scale, isn't a feature of a naturally occurring universe, but a clue to its artificial origin? This leads us to one of the most debated and culturally resonant ideas on our list, the simulation hypothesis, a theory that proposes our entire reality, with all its quantum quirks, might be an immensely sophisticated digital construction, and that the fluctuations we detect are merely the background processing noise or the pixelation of the simulation itself. The core of this idea is both ancient and modern. Philosophers have long pondered the nature of reality and whether our experiences are genuine or a grand illusion, from Plato's allegory of the cave to Descartes' evil demon. The modern simulation argument, most famously formalized by philosopher Nick Bostrom in 2003, gives this ancient skepticism a technological twist. Bostrom's trilemma posits that at least one of three propositions must be true. First, that almost all civilizations at our level of development go extinct before becoming technologically mature. Second, that almost all technologically mature civilizations lose interest in creating ancestor simulations. Or third, we are almost certainly living in a computer simulation. The logic is based on a simple extrapolation of computing power. If a civilization ever reaches a post-human stage capable of harnessing the energy of entire stars to power computers, and if they have any desire to run detailed simulations of their ancestors, they could potentially run astronomical numbers of them. The number of simulated minds would vastly outnumber the number of biological original minds. Therefore, if such simulations are possible and desired, the statistical probability that we are one of the few original civilizations rather than one of the countless simulations approaches zero. So how do quantum fluctuations fit into this digital picture? In any simulation, there are inherent limits. A video game, no matter how advanced, has a finite resolution. If you zoom in far enough on a digital image, you eventually see the individual pixels. The theory suggests that the Planck scale, that unimaginably tiny distance of 10 to the negative 35 meters, could represent the fundamental resolution of our reality. It's the smallest possible pixel in the cosmic simulation, the point beyond which no further detail is rendered. The violent chaos of the spacetime foam at this scale could be the graphical glitching or the computational rounding errors that occur when the simulation tries to process physics at its maximum resolution limit. Those virtual particles popping in and out of existence, they might not be borrowing energy from a quantum field, but rather, they could be artifacts of the simulation's rendering process, brief data fluctuations or background processes running in the cosmic computer's memory. This perspective even offers a potential, albeit speculative, handwave at the cosmological constant problem. The catastrophic mismatch between the predicted and observed energy of the vacuum could be explained as a simple variable choice by the programmers. The laws of physics in our universe wouldn't need to be derived from some elegant, fundamental theory. They could be chosen parameters, lines of code that were set to values that allow for interesting complexity like galaxies and life to form. The value of the cosmological constant isn't a puzzle to be solved. It's a dial that was turned to a setting that prevents the simulation from crashing or becoming too boring. The fact that it seems fine-tuned for life isn't a miracle, it's simply a selection effect. We exist in a simulation that is stable and complex enough to support simulated observers. Naturally, this idea is met with intense skepticism from many physicists. The main criticism is that it is fundamentally untestable and unfalsifiable. It doesn't make any specific predictions that differ from a genuine universe. It simply offers an alternative, metaphysical explanation for the same observed phenomena. Furthermore, the computational resources required to simulate every quantum fluctuation in every atom of every star in a universe of trillions of galaxies are mind-boggling, perhaps exceeding any plausible energy source even for an advanced civilization. However, some theorists counter that the simulation wouldn't need to render everything in perfect detail all the time. It could use clever optimization techniques, like the level of detail rendering used in video games, where high-resolution processing is only applied to the areas being observed. The peculiarities of quantum mechanics, where particles exist in a haze of probability until measured, could be seen as a form of this processing power is only devoted to resolving a definite state when absolutely necessary. Whether a captivating thought experiment or a genuine possibility, the simulation hypothesis forces a profound reconsideration of reality. suggesting that the quantum foam might not be the foundation of the cosmos, but simply the texture of its code. But this journey into the very fabric of reality and information brings us to perhaps the most intimate and speculative frontier of all, the enigmatic connection between our own conscious awareness and the quantum realm. We've explored how fluctuations might shape the cosmos and influence evolution, but could they be actively involved in generating the phenomenon of consciousness itself? This is the profound and deeply controversial proposal of the orchestrated objective reduction theory, or ORCH, which suggests that the seat of human consciousness may lie within the intricate architecture of our own brain cells, tapping directly into the universe's fundamental quantum vibrations. To understand this radical idea, we first need to look inside a neuron. The mainstream view in neuroscience treats the brain as a complex classical computer, where consciousness emerges from the sheer computational complexity of neural networks firing. But this approach hits a formidable wall known as the hard problem of consciousness. Why should any amount of electrical and chemical processing produce a subjective, inner experience? Why does the firing of certain neurons feel like the color red or the sound of a symphony? It's a problem that seems to defy any purely mechanical explanation. This gap led physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff to propose a breathtaking alternative. They argue that the brain isn't a classical computer, it's a quantum one, and the source of its quantum power lies in structures called microtubules. Imagine the skeleton of a brain cell. Microtubules are tiny, cylindrical protein structures that form this internal scaffolding, giving the cell its shape and helping to transport vital materials. Hameroff proposed that these are not just passive beams and girders. Their precise, lattice-like structure could be perfectly designed to protect and harness quantum effects. Within these microtubules, electrons could become delocalized, existing in a quantum superposition of states essentially, performing multiple calculations at once. This is where Penrose's contribution becomes essential. He had long argued that the collapse of a quantum wave function, the moment a superposition chooses a single state, is not random but is an objective process driven by gravity. When the superposition within a microtubule becomes too large, its own mass energy causes a spontaneous and instantaneous collapse. According to ORCH, this moment of collapse isn't just a physical event, it is a discrete moment of conscious experience. A single bit of awareness, our stream of consciousness then, would be a symphony of these orchestrated collapses happening across vast networks of neurons conducted by the brain's biological processes. And what provides the background hum, the fundamental randomness that fuels these collapses? The theory points directly to the quantum fluctuations of spacetime itself at the Planck scale. The seething, chaotic energy of the quantum gravity field could be interacting with the microtubules, influencing the timing and nature of these collapses. In this view, our consciousness isn't locked away inside our skulls. It is a dynamic interplay between the neurobiology of our brains and the very fabric of the universe. We are not just observers of the quantum world, we are participants with our minds intimately connected to the foundational tremor of reality. However, it is crucial to understand that this theory remains highly controversial and is rejected by a significant portion of the scientific community. The criticisms are formidable and rooted in solid physics. The brain is widely considered to be a warm, wet, and noisy environment. Quantum states are incredibly delicate, and the constant jostling of molecules at body temperature should, according to conventional wisdom, cause any fragile quantum coherence to decohere, to vanish in a fraction of a second, far too quickly to play any meaningful role in neural processes. Critics argue that any quantum effects would be instantly scrambled, making the brain a profoundly classical object. They maintain that the incredible complexity of neural networks is sufficient to explain consciousness without needing to invoke quantum mechanics, often dismissing ORCH as a modern form of quantum mysticism. Yet, despite the criticisms, the theory persists and continues to evolve, fueled by its audacious attempt to solve the hard problem. Proponents point to some intriguing, though not yet conclusive, evidence. Studies on the mechanisms of general anesthesia, for instance, show that anesthetic gases seem to act by shutting down quantum vibrations within microtubules, effectively turning consciousness off without causing brain damage. This suggests that these quantum processes might be more than just a theoretical curiosity. Furthermore, some experiments have even reported finding vibrations in microtubules at frequencies that align with the theory's predictions. Whether or ultimately proves to be correct is still an open question, but it represents a monumental effort to bridge the gap between mind and matter, suggesting that the inner light of consciousness and the outer darkness of the quantum vacuum might be two expressions of the same deeply mysterious reality. Now, as we journey deeper into the quantum landscape, we encounter a series of numerical riddles so precise they seem to defy mere chance. These are the cosmic coincidences, a collection of staggering numerical relationships between the largest scales of the cosmos and the smallest scales of the quantum world, relationships that have left physicists both fascinated and deeply unsettled. It's as if the universe has left us a series of cryptic clues, written in the language of mathematics, hinting that the cosmos and the quantum are not separate realms but are intimately, and perhaps fundamentally, linked. Consider one of the most famous of these puzzles, a comparison so audacious it feels almost mystical. The ratio of the gravitational force to the electromagnetic force between two protons is a number so small it's almost beyond comprehension, roughly 10 to the negative 36. Now take the size of the observable universe, an immense scale we call the cosmic horizon, and compare it to the smallest possible scale in nature, the Planck length. That ratio is a number so large it's also almost beyond comprehension, roughly 10 to the positive 60. The astonishing fact is that the square of the first number, 10 to the negative 72, is eerily close to the inverse of the second number. It's a numerical whisper that suggests the strength of gravity might be directly related to the size and age of the universe itself. Why should the fundamental strength of a force that governs the attraction between apples and planets have anything to do with the total amount of space contained within our cosmic horizon? This isn't just a curiosity, it's a profound enigma that suggests gravity might not be a fixed, eternal constant, but something that evolves with the expanding cosmos. Another breathtaking coincidence involves the energy stored in empty space. The mass of the observable universe is estimated to be around 10 to the power of 53 kilograms. If you were to take that entire mass and convert it into pure energy using Einstein's famous equation, you would get a number. Now, take the measured energy density of the vacuum, the tiny nudge of dark energy that's accelerating the universe's expansion, and multiply it by the volume of the observable universe. You get almost exactly the same number. It's as if the total energy of matter in the cosmos is precisely balanced by the total energy of nothingness, of empty space itself. This could be a meaningless numerical fluke, or it could be a profound clue pointing toward a deeper principle of cosmic balance, a universe where something and nothing are two sides of the same coin. These numerical relationships don't stop at the largest scales. They reach right down into the world of atoms and particles. The famous large number coincidence, first noted by physicist Paul Dirac, observes that the ratio of the age of the universe to the time it takes light to cross an atom is about 10 to the power of 40. This same enormous number, 10 to the 40, also appears as the square root of the number of particles in the observable universe and even pops up in the ratio of the electrical force to the gravitational force inside a hydrogen atom. It's as if this specific colossal number is a fundamental constant of creation, a magic number that connects the era we live in, the number of particles that exist, and the very forces that bind them all together. For Dirac, this was too significant to ignore. He proposed that what we perceive as constants, like the strength of gravity, might actually be slowly changing over cosmic time, evolving in such a way that these large number ratios are maintained. This idea of varying constants, while not mainstream, remains a tantalistic possibility that some physicists continue to explore. So, are these cosmic coincidences just that, coincidences? The skeptical view is that in an infinite universe, or even just a very large one, seemingly miraculous numerical alignments are bound to happen purely by chance. We are pattern-seeking creatures, and we might be connecting dots that have no real physical connection, crafting a narrative of significance where there is only random noise. This is a healthy scientific attitude, and many physicists argue that pursuing these numerical relationships is a form of numerology unless it leads to testable, predictive theories. Yet, the persistence and precision of these relationships are difficult to dismiss entirely. They are like finding that your phone number is encoded in the first 10 digits of pi. It feels too specific, too designed to be entirely random. This leads to the more compelling interpretation that these coincidences are not accidents at all, but signposts. They may be the observable shadows of a much deeper, unified theory of physics, one that seamlessly weaves together the quantum and the cosmic. In such a theory, the constants of nature wouldn't be arbitrary numbers plugged into equations. They would be dynamic values that emerge from the fundamental structure of the universe. The strength of gravity, the energy of the vacuum, and the size of the cosmos would all be interrelated aspects of a single, coherent whole. The numerical whispers we detect would be the natural outcome of this deeper reality. The way the harmonious notes from a guitar string are the natural outcome of its tension, length, and density. We are hearing the music of the universe, but we haven't yet fully deciphered the score from which it's played. Ultimately, these cosmic coincidences challenge us to decide what kind of universe we believe we live in. Is it a universe of stark separation, where the realm of the impossibly small and the realm of the impossibly large operate by independent rules, their numerical harmonies nothing more than a fleeting cosmic melody that will fade as the universe expands and changes? Or is it a universe of profound connection where every scale is linked, where the quantum fluctuation in an atom and the fate of a galaxy are part of a single unfolding story? These numerical riddles, etched into the fabric of reality, may be our best hint that the latter is true, that we are living in a cosmos where everything, from the smallest whisper to the largest echo, is part of one magnificent, interconnected whole. Yet for all its profound implications, this staggering mismatch between prediction and observation is more than just a mathematical headache. It represents a fundamental crisis at the very heart of modern physics, a problem so severe it has been called the vacuum catastrophe. Imagine calculating the weight of a single snowflake using the most advanced equations we have and concluding it should weigh as much as 1 billion suns. That is the scale of error we are confronting here. The theoretical value for the vacuum energy is around 10 to the power of 113 joules per cubic meter, an energy density so unimaginably dense it would have torn the infant universe to shreds in a fraction of a second. But when we look out at the cosmos with our most powerful telescopes, the actual measured value of this energy, what we call dark energy, is almost zero, about 10 to the power of -9 joules per cubic meter. The difference between these two numbers is a factor of 1 followed by 121 zeros. To put that number into perspective, it is a greater difference than the scale between the size of a single proton and the size of the entire observable universe. It is, by a monumental margin, the worst theoretical prediction in the entire history of science. This isn't a simple case of being off by a little bit. This is a screaming paradox that tells us, in no uncertain terms, that we are missing something absolutely fundamental in our understanding of how the universe works. Our two most successful theories, the quantum mechanics of the very small and the general relativity of the very large, are at war over the nature of nothingness itself. Quantum field theory tells us the vacuum should be bursting with energy, while general relativity, when fed that energy value, predicts a universe that could never have formed stars, planets, or people. The fact that we exist to even notice this problem means our theories, for all their predictive power, are incomplete. We are like watchmakers who have built two exquisitely precise timepieces, only to find they tell completely different times, and we have no idea why. The vacuum catastrophe is the alarm bell ringing from both of them at once, a clear signal that a deeper, more unified theory of quantum gravity is needed to resolve this epic disagreement. It is the single greatest clue we have that our current physics is merely a shadow of a much more profound and beautiful reality waiting to be discovered. We've journeyed from the birth of galaxies to the nature of consciousness, all guided by the invisible hand of quantum fluctuations. But this exploration forces us to confront perhaps the most fundamental question of all, one that has perplexed philosophers and physicists for millennia: what is nothing? We throw the word around so casually, an empty room, the void of space, but when we apply the ruthless lens of quantum mechanics, the very concept of nothingness begins to unravel, revealing a reality far stranger and more active than we ever imagined. For centuries, the philosophical ideal of nothing was a perfect vacuum, a complete and total absence of anything. No matter, no energy, no forces, no fields. A pure, featureless void of non-existence. This was the nothing of the ancient Greeks, the void that atomists like Democritus believed atoms moved through. It was a stage, an empty container waiting to be filled. Even for Isaac Newton, space was an absolute, unchanging arena, a fixed background against which the drama of physics played out. True nothing in this view is simple. It is zero. It is the ultimate ground state, the complete lack of any activity or property. But quantum mechanics shatters this classical intuition. As we've seen, the vacuum of space is not passive or empty. It is a seething, chaotic foam, a quantum field in its lowest possible energy state. This is not nothing in the philosophical sense. It is a something with very specific properties. It has structure, it has energy, it has fluctuations, it can exert force, as the Casimir effect proves. So, if this isn't nothing, what is? We're left with a profound dilemma. The closest thing to nothing that actually exists in our universe is this quantum vacuum, and it is teeming with activity. This forces us to refine our definition. Perhaps true nothing is an abstract concept, a mathematical ideal that cannot and does not exist in physical reality. The universe seems to abhor a true vacuum. There is always this background hum, this zero-point energy that can never be removed. This leads to a breathtaking possibility, one that turns the question of existence on its head. If the quantum vacuum is the new nothing, then our entire universe, with all its galaxies and stars and people, might be seen as a relatively minor fluctuation on top of this vibrant, energetic ground state. We are not something emerging from nothing, but a specific pattern of something emerging from a different, more fundamental kind of something. The question, why is there something rather than nothing, might be based on a false premise. There has always been something, the quantum fields, and our universe is simply one particular excited state of those fields. This doesn't make our existence any less miraculous, but it reframes the miracle from one of creation from absolute zero to one of organization from a pre-existing chaotic potential. Philosophers and physicists alike are now left grappling with this new definition. Is the quantum vacuum the true void, or is it merely the lowest rung on the ladder of existence? Some argue that the fields themselves are a form of something, and that the quest for absolute nothing must continue into the realm of metaphysics. Others suggest that the properties of the quantum vacuum are so fundamental that they define existence, and therefore, this is what nothing actually looks like. It's a dizzying shift in perspective, where nothing isn't an empty box but a living, breathing foundation, pregnant with potential, from which everything we know and are has spontaneously arisen. The quantum fluctuation isn't a violation of nothingness. It is the fundamental nature of what we mistakenly called nothing all along. While these are profound philosophical questions, physicists are not content to simply wonder. They are building extraordinary machines to interrogate the quantum vacuum directly, to listen to its faintest whispers and map its hidden topography. This brings us to the thrilling experimental frontiers where theory meets reality, where scientists are devising ever more ingenious methods to detect and measure quantum fluctuations with breathtaking precision, pushing the very limits of what we can observe. The classic Casimir effect, once a stunning theoretical prediction, is now a well-established laboratory phenomenon, but scientists are far from finished with it. Modern research has moved far beyond simply confirming the attractive force between two plates. Researchers are now experimenting with exotic materials and complex geometries to probe the quantum vacuum in new ways. Imagine constructing microscopic gears or intricate shapes using advanced nanotechnology, and then observing how the Casimir force acts upon them. By using materials with different magnetic or electrical properties, so-called metamaterials engineered to have responses not found in nature, scientists can actually manipulate the Casimir force, turning attraction into repulsion. This isn't just a parlor trick, it provides a powerful new testing ground for quantum electrodynamics. If the force behaves differently than predicted with these advanced materials, it could reveal new physics, perhaps even hints of extra dimensions or other exotic phenomena hidden within the vacuum structure. These experiments are transforming the Casimir effect from a simple demonstration of quantum foam into a precision tool for exploring the fundamental fabric of space. Beyond manipulating metal plates, some of the most exciting work is happening in the realm of ultra-cold atoms. By using lasers to cool clouds of atoms to a fraction of a degree above absolute zero, physicists can create a state of matter known as a Bose-Einstein condensate, where quantum effects become visible on a macroscopic scale. In this bizarre and beautiful environment, researchers can effectively simulate the conditions of the early universe or create analog black holes. By carefully perturbing these condensates, they can watch how quantum fluctuations ripple through the system, growing and evolving in ways that mirror the amplification of fluctuations during cosmic inflation. These tabletop universes allow us to run experiments that would be impossible on a cosmic scale, providing a unique window into how randomness at the quantum level can forge the large-scale structure of reality. It's a breathtaking convergence of the immensely small and the immensely large, all contained within a vacuum chamber on a lab bench. The ultimate goal, however, remains the direct detection of quantum gravity's signature, John Wheeler's spacetime foam. While we cannot yet probe the Planck scale directly, astronomers are using the universe itself as a giant particle detector. One ingenious method involves studying the light from incredibly distant astrophysical sources, such as gamma-ray bursts or active quasars billions of light-years away. The idea is that if spacetime is truly foamy at the fundamental level, it should act like a subtle fog for light. Photons of different energies would be affected slightly differently as they travel through this quantum graininess over cosmic distances. A high-energy gamma-ray photon might be delayed by a minuscule amount compared to a lower-energy radio wave from the same event. These travels across the universe are the most sensitive interferometers we have. By comparing the arrival times of these different photons with exquisite precision using telescopes like the Fermi Gamma-Ray Space Telescope, scientists are placing ever tighter constraints on the possible foaminess of spacetime. So far, the universe appears remarkably smooth, even over these vast journeys, suggesting that if foam exists, its effects are even smaller than some models predict. But the search continues, with each new observation helping to chip away at the possibilities and bring us closer to understanding the true quantum nature of gravity. Looking to the future, the ambition grows even more audacious. Proposals for gravitational wave detectors in space, like the Laser Interferometer Space Antenna or LISA, promise not just to listen for collisions of black holes, but to use those ripples in spacetime as a new kind of probe. The incredibly precise measurements required could potentially reveal how quantum fluctuations affect the fabric of spacetime itself on the largest scales. Other theorists are designing experiments that use superconducting qubits, the building blocks of quantum computers, to try and detect the hypothetical particles associated with quantum gravity. The common thread running through all these endeavors is a drive to move beyond theory and truly touch the quantum vacuum, to measure its properties and understand its role as the foundational substrate of everything. Each experiment, whether it succeeds or fails, carves away another piece of the unknown, bringing us closer to answering the most profound question of all: what is the true nature of the reality we inhabit? Yet for all these ingenious experiments, the ultimate answers to the deepest puzzles of quantum fluctuations likely lie not in any single observation, but in a new theoretical framework, a final, unifying theory of quantum gravity that can seamlessly weave together the laws of the very small and the very large. This grand quest is the driving force behind some of the most brilliant and ambitious minds in physics today, who are exploring radically different paths in the hope of finally resolving the paradoxes we've encountered. Three of the most promising approaches, string theory, loop quantum gravity, and emergent gravity, each offer a strikingly unique vision of reality, and each attempts to tame the chaotic quantum vacuum in its own remarkable way. String theory proposes a breathtakingly elegant solution to the problem of quantum fluctuations by fundamentally changing what we believe the universe is made of. Imagine zooming in on an electron, past the point of it being a dimensionless point particle, and discovering that it isn't a particle at all, but a tiny, vibrating loop or string. In this view, every different type of particle, electrons, quarks, photons, even the hypothetical graviton, is just a different note, a different vibrational pattern played on these incredibly tiny strings. The frantic energy of the quantum vacuum, with its virtual particles popping in and out of existence, is reinterpreted as the constant, lowest energy hum of these strings. This simple shift in perspective has a monumental consequence. It smooths out the violent, infinite calculations that plague traditional quantum field theory when it tries to include gravity. The strings, by having a finite size, prevent physics from breaking down at the infinitesimally small Planck scale. Furthermore, string theory naturally requires the existence of extra dimensions of space curled up into shapes too small for us to see, and the specific way these dimensions are folded could potentially explain the incredibly small, non-zero value of the cosmological constant. The vacuum energy isn't a calculation gone wrong. It's a specific outcome of the way the strings vibrate within the full, higher dimensional geometry of the universe. Taking a completely different path, loop quantum gravity approaches the problem not by changing the ingredients, but by reimagining the very stage they perform on. Instead of smooth, continuous spacetime as envisioned by Einstein, this theory proposes that space itself is woven from a fabric of finite, discrete loops. Think of it not as a smooth sheet of rubber, but as a chainmail mesh, with each individual link representing the smallest possible unit of area and volume. At the Planck scale, spacetime is granular, a network of these interconnected loops. In this framework, the quantum foam isn't a chaotic sea of virtual particles in a void. It is the dynamic, evolving structure of spacetime itself. The fluctuations are the loops constantly changing their connections, a cosmic dance of geometry where tiny regions of space pinch off and reconnect. This granularity provides a natural cutoff that prevents the disastrous infinities of the vacuum energy calculation. There is simply no such thing as a wavelength shorter than the Planck length because there is no space for it to exist in. The energy of the vacuum becomes finite and calculable within this discrete structure, offering a potential pathway to resolving the cosmological constant problem by fundamentally changing our understanding of what space is. A third and perhaps most radical class of ideas suggests that we've been thinking about gravity all wrong. Emergent gravity theories propose that gravity is not a fundamental force at all. It doesn't need to be quantized because it isn't there in the basic laws of physics. Instead, gravity and the curvature of spacetime along with it emerges from the collective behavior of something more primitive. This is analogous to how the temperature of a gas emerges from the chaotic motion of countless molecules. You can't point to a single molecule and ask for its temperature. In the same way, theories like Eric Verland's entropic gravity suggest that gravity is an entropic force, a consequence of the universe's natural tendency to increase disorder or entropy. In this view, the dark energy driving the universe's acceleration might not be a mysterious energy inherent to space, but a reflection of the way information is stored on the cosmic horizon. The quantum fluctuations would then be the microscopic degrees of freedom from which gravity and spacetime themselves condense, much like water droplets condensing from random water vapor molecules. This would mean that the vacuum catastrophe is a mirage born of a category error. We are trying to apply a concept from fundamental quantum theory to a force that is itself emergent and statistical. These three path strings, loops, and emergence represent the cutting edge of theoretical physics, each with its own passionate advocates and formidable challenges. String theory boasts incredible mathematical beauty and naturally includes gravity, but it predicts a vast landscape of possible universes, making unique predictions for our own incredibly difficult. Loop quantum gravity provides a compellingly direct quantization of space itself, but has struggled to show how smooth spacetime emerges from its granular building blocks on large scales. Emergent gravity offers a stunningly new perspective that could dissolve old problems, but it remains in its early stages of development, with its full mathematical structure still being explored. What makes this intellectual pursuit so thrilling is that these are not just minor tweaks to existing ideas. They are complete reinventions of our core concepts of space, time, and matter. They remind us that the next great leap in understanding will likely require us to let go of our most deeply held intuitions and embrace a universe far stranger and more wonderful than we have yet dared to imagine. The resolution to the mystery of quantum fluctuations won't just be an answer. It will be a revelation, showing us that the chaos of the vacuum was never a problem to be solved, but a profound clue pointing toward a deeper, hidden order. From the ghostly whispers of virtual particles in a vacuum to the very birth of galaxies, we've journeyed through a cosmos built upon a foundation of quantum uncertainty. We've seen how these infinitesimal fluctuations are not mere background noise but the central architects of reality, shaping everything from the fate of black holes to the arrow of time itself. They are the seeds from which the entire cosmic tree grew, the subtle grain in the fabric of spacetime, and perhaps even the source of our own conscious experience. Whether through the validated predictions of Hawking radiation and the Casimir effect or the mind-expanding possibilities of the holographic principle and cosmic simulation, these quantum jitters force us to confront the most profound questions about existence, causality, and our own place in the universe. What's truly astonishing is the sheer range of ideas this one phenomenon inspires. On one end, we have the solid, testable bedrock of established science, where quantum fluctuations are a predictable and essential part of our most successful theories. And on the other, we have the wildly speculative frontiers where they become the gateway to multiverses, the engine of consciousness, and the potential pixelation of a simulated reality. This incredible spectrum, from hard-won experimental data to breathtaking philosophical conjecture, shows just how deep this rabbit hole goes. It reveals that the tiniest disturbance in the nothingness of empty space might indeed hold the ultimate keys to the largest mysteries, the origin, structure, and ultimate fate of all we see. This journey doesn't end with this video. In many ways, it's just beginning. The conversation about what reality truly is continues in labs, in universities, and in the minds of curious people everywhere. So now we want to hear from you. Which of these theories resonated most deeply? Does the participatory universe of John Wheeler ignite your imagination? Or does the stark, elegant mathematics of the holographic principle feel like a more compelling path to the truth? Perhaps you're drawn to the daring idea that our consciousness is intertwined with the quantum foam itself. Share your thoughts in the comments below. Let's keep exploring this strange and beautiful quantum world together.